Okay. So by the end of this course, you should be able to critically acquire and develop an in-depth understanding of when, why, and how to use a variety of statistical techniques and also tools and techniques of data science. All right. And also compare and contrast the basic technique for representing uncertainty, qualitative representation, and also critically assess and demonstrate rule-based, case-based, and more model-based reasoning. Okay. So these are the topics we'll be having a look at. So today we'll be having a look at data types, describing data, right? Probability, we'll touch on probability, sampling distribution, hypothesis testing, z-tests, t-tests, and for two populations. We'll be looking at test of independence, that is chi-square, all right? And then regression, that is simple regression, multiple regression, and also logistic regression. All these topics underpin most of the models we'll be using, okay, in data science. So we'll see where this can be applied. Can you just give me a minute, please? Okay, sorry, I'm back. So yeah, we'll be having a look at all these topics. And like I said, we'll get to understand why these topics are relevant to the models that we'll be building. So having a grasp of these topics, whenever you have the opportunity to use any kind of models in data science, you will understand the mathematical reasonings for this. Okay, all right. So that will be the focus of this model, right? Any questions? Any questions on this? Mandele, Ophoria Manfo, can you hear me now? Is it better?
Yes, Nana, I can hear you now.
All right. So let's zoom
Nana,
straight. Yes.
in your honest opinion, this one and the R, which one is difficult?
What do you mean by this one in the R?
Like mathematical functions. Eh,
But what is R used for? R is also can be used for all these. R is just a
Okay.
medium of R can be used for data science or statistics.
Okay.
Probably you mean the coding aspect and stuff like that.
Yeah. Yeah.
Oh, whether it is mathematical functions you are using, if you are to use R, you will use coding to do that. Okay. But here, our
Okay.
focus is not really about using R. Our focus is to understand the uh, uh, the topics. Okay, the
Okay.
reason behind the topics. Okay.
Oh, okay. The foundations.
So
Okay.
the R that we use, don't see it as uh, R is not confined to only data science. Okay, one of the very big strengths of R is statistics. Okay, so that is why when it comes to statistics, R is much more effective than using Python. Okay, but
Okay.
Python has a broader use. Okay, apart from data science, you can use it for other stuff. Okay, which is not really like data science. Okay, so um, that's why having the two is important. Right? So the kind of
Thank you.
statistics that R can do, uh, Python can do, but it's not as concise as R when it comes to statistics. Okay. All right. So yeah. So this is what we will do. Why the ones that we did is it difficult? The data, the descriptive analytics that we did. All you have to do is to practice and then understand. Okay. All right. So let's zoom straight into data types and then describing data. Okay. Please, can you see my screen? The new one, the slides. Can
No,
you also? Okay. So can you see the study objectives?
I can see topics.
Oh, you are still seeing the topics.
Yes. Yeah, I can see the first unit now.
Okay. All right. So we'll be looking at data types and then describing data. Okay. So after completing this session, we'll get to distinguish between different data types. Okay. Explain the measures of center. Okay. Explain the measures of center. So we'll talk about mean, median, mode, and also we'll look at the spread of data in terms of its variance, standard deviation, and interquartile range. Okay. And then we see how we can represent numeric and categorical data, right? We've seen some of them already, okay, when we're doing data visualization, but here you get to understand the mathematical reasoning behind it. And then to compute and interpret the score of a data point. So basically, this is what we'll be doing today. Okay. And my assumption is that uh, even if you've not done some stuff, for most of us, this will be a revision of what we've done at the undergraduate level. Okay. So it will give us probably a better understanding of these topics. Okay. So we will take it step by step. All right. Step by step. And we'll make sure that we move everybody along with us. that we don't leave anybody behind. So feel free to stop me anywhere that you don't understand. I'll be glad to help. So in terms of data types, we have qualitative data and then quantitative data. So qualitative data is the same as what we call the categorical data. Now, this categorical data can either be nominal or ordinal. Okay. So when we say that it is nominal, which means it is unordered. Okay, so we can have groups of, say, married people, unmarried people, male, female, that kind of thing. Okay, so in that sense, they are categorical data, but they are not numbered or they are not ordered. So which means that they can come in any form. You can start with unmarried and let's say married or female, male or male, female. Okay. In the same vein, we have categorical data that is ordered. Categorical data that is ordered. Okay. So in such situations, the arrangement is important. Okay. For instance, when you take a survey, you can have options like strongly agree, somewhat agree, neither agree or disagree, somewhat agree, strongly agree. Okay, so they are ordered in that sense. Okay, so in terms of qualitative data, we have nominal and then ordinal. Okay, so when it is nominal, it is not ordered. When it is ordinal, okay, so you can see the ordered in there. Okay, so when it is ordinal, that means that it is ordered, but they are all categorical data. Okay, any questions on qualitative data or categorical data?
Yeah.
Yeah.
Nana, please. Is there any qualitative data that falls outside of these two?
Not really, no. Not that I know of. So it is either nominal or ordinal. Okay.
What about you are maybe collecting the data and you ask a person why, and the person tends to give you sentences, like a paragraph, what it falls under nominal?
Okay, so it depends. It depends upon the information that you want. Let's say you are collecting data and then you ask of why. Okay. Now, depending upon the type of data you are collecting, if it is a qualitative data, for instance, normally the answers that they give to you, you code them into themes. Okay. I don't know whether you've heard of thematic analysis.
I do.
Yeah, so you code them into themes. So these themes could be like one word to describe something. So if they are not ordered, then in that sense, it becomes a nominal data, okay? So
okay.
Even if they give you sentences, you can code all of them into specific themes, put everything into groups. Okay, so in that sense, they become nominal data. However, you ask the why, and then that's why I'm saying that it depends upon the kind of data you are collecting. And then you put them into themes. The themes that you are putting them into could be ordinal, all right? So it depends upon the kind of data you are collecting. But to simplify it, the ones that have where intensity or there is some levels in it, that is when it becomes ordinal. Where there is no levels in it, anyone can come first, then it becomes nominal. Okay, if you simplify,
okay,
that's what it comes to.
Thank you.
Okay. Now, in terms of quantitative data is also known as numeric data. Okay. So these ones will be discrete variables or continuous. variables. Okay, so discrete are the ones that you can count. Let's say the number of pets, the number of packages shipped, okay, the number of tables, the number of chairs. These ones, they are distinct and they can be counted. All right. Now, in terms of numeric data too, we have what we call the continuous or measured. So these ones cannot be counted. They are not counted, like checking the speed, okay, or the time spent walking in a park, okay, or the height of somebody, okay. These things are what we call continuous variables, okay. So these ones are normally measured. They are not counted, okay. So any variable that you measure, okay, it's a numeric variable. However, it is continuous. It is not discrete. And the ones that you can count, the distinct ones that you can count, okay, these are what we call discrete variables. Okay. Please, any questions about qualitative and quantitative data? So quantitative, as the name suggests, is numeric. And to draw your attention to one thing too, with the qualitative data, sometimes you could have numbers representing them, but that doesn't necessarily make them numeric. Okay, so for instance, the nominal data, you can have 1 representing married and then 0 representing unmarried. Okay, it is still a nominal data. It doesn't, the fact that we have used 1 and then 0 doesn't make it a numeric data. Please, do you get the understanding?
Yes.
Okay, all right.
I have a question.
Yes, please go ahead.
May I please get more examples on the qualitative
But
data?
qualitative?
Yeah, I'm quite confused because I was thinking maybe you're looking at, let's say, 10 married people and then 15 married people, but then I'm realizing it's not like that. So if I could get more examples so that I could be more clear.
Okay, so let's say you are looking at marital status. Okay?
Yes, please.
So you have married. Let's say you can have, let's say you are filling a form, they ask of your marital status. Single, married, divorced. Okay? So let's say you have these 3 options. Now, in terms of order, none of them comes first. None of them, you can't say that unmarried is greater than married or married is greater than divorced. Okay? But when you come to ordinal, something like strongly disagree is higher than somewhat disagree, isn't it? Or strongly agree is higher than somewhat agree. So where you have kind of levels in it, then it becomes ordinal. It is ordered. All right? Okay, so where it is not, so at that point, don't be looking at the number of, you're not looking at the counts. You are just looking at the groups that you have. If the groups are ordered, then it becomes ordinal. If the groups are not ordered, so let's say small, smaller, smallest, it is ordered, isn't it?
Yes, it is.
Big, bigger, biggest, it is ordered. But if you have, let's say you can have fruits, apples and oranges, they are not ordered, okay? But when you take apple, you can look at various sizes of apple. Let's say big, bigger, biggest, okay? In that sense, the apple alone, within the apple, there are levels of the apple. Have you seen? So in that sense, it becomes ordered. Okay.
All right.
Okay.
Thank you.
You're welcome. So like I said, you can have married or unmarried, which is nominal. It could be represented by 1s and 0s. You could have gender represented by, let's say, 1s and 2s. Let's say 2 could represent male, 1 could represent female, or otherwise. So in that sense, it doesn't make it a numeric data, okay? It is still categorical, just that it is being represented by numbers, right? So you know the difference. Now, when it comes to ordinal, so you see that it is ordered. So sometimes, like you have in a normal survey, let's say the strongly agree will be 1, disagree will be 2, neither agree or disagree will be 3. Okay, somewhat disagree will be 4, and so forth. Okay. All right. So let's look at the ways in which we can describe qualitative data. The ways we can describe qualitative data. Please, just a minute. Okay. Yeah, so let's look at the ways we describe qualitative data. So it could be in terms of class, okay? We could look at it from the perspective of class frequency or class relative frequency or class percentage. So we will have a look at all of them into detail. So when we talk about class, we're looking at the category of the observation that we are considering, okay? So in terms of class frequency, when you take a particular class, okay, how many observations can you count in that particular class? Okay, so that will give us the class frequency. Okay, and then the class relative frequency. This one is in terms of the total. Okay, so you look at how many times they appear divided by the total number of observations. Okay, so if you want to look at the class percentage, we just multiply the class relative frequency by 100%. So let's see how this is treated further. Okay, so have a look at this pie chart. So I told you that in terms of data visualization, data scientists, we are not so much keen with pie charts. Okay, nevertheless, you should know how it is calculated. So just in case you meet it anywhere, then you are able to deal with it. Okay, but it's not something we normally use in our data visualization. So a pie chart takes the categorical data and shows the percentage of individuals that fall into each category. So let's say on your right, you have comedy, action. So in terms of movies, okay? So comedy, action, romance, drama, sci-fi, okay? So each of these categories, you have some number of movies, giving us 20 movies. So let's say if you want to calculate the percentage, okay, of each group, okay, let's say comedy appears 4 times, okay? All right, if you want to calculate the proportion of comedies, then it will be the 4 divided by the total number of movies. That will be 4 over 20. That gives you 20%. Okay, so you can do for the other movies, and then you have on the right, in terms of percentage, you have comedy being 20%, action 25%, romance 30%, drama 5%, sci-fi 20%. Okay, you could also do it in terms of degrees. Okay, so for a typical circle, we have 360 degrees. Okay, so if you want to find out the proportion of comedy, okay, instead of multiplying it by 100, okay, it is 4 over 20 times 360. Okay, just a minute, please. Okay, so in terms of degrees, it can be done by multiplying the number for each group divided by the total times 360. Okay, kindly put on the microphone. Okay, all right. So whether it is percentage or in terms of degrees, this can be done. Okay, this can be done. And then normally is the sum of all the slices of the pie, okay, should be 100%, okay, or close to it. Okay. So because of this rounding of errors, sometimes it's not exactly as it is. That's why you don't want to, we don't put so much weight on pie charts, okay? But at least you know how it is calculated. Please, any question on the pie chart? On the calculation? So whether we are using percentage or degrees, you just take the frequency for each group divided by the total. If it is 100% you are using to display your pie chart, then you multiply it by 100. If you want to use in terms of degrees too, then you multiply it by 360, then to give you the proportion of the degrees or the percent. Okay. Any questions on the pie chart? All right. Let's look at other plots. Okay. So another way by which we can describe qualitative data is to use the cumulative frequency curve. Okay, cumulative frequency curve. So here we put, what we do is that we put various groups. So here, in terms of age, let's say we have between 21 to 24 group, 25 to 28 group, 29 to 32 group, 33 to 36 group, and then 37 to 40 group. Now, within each of the groups, okay, how many times do you have observations that fall into this group? That gives us the frequency, okay? So the frequency of each group is what you have in the second column. Now, if you want to calculate the cumulative frequency, then we add them up as we go along. So let's say from the lowest, that is from 21 to 24 group, the frequency was 3, okay? So that means that we are starting from 3. The cumulative frequency is 3, all right? So when we come to the 25 to 28 group, the frequency is 7. So since we have 3 already, we add 3 to 7 to give us 10. That is the cumulative frequency, okay? Now, when we come to the next group, that is 29 to 32, the frequency is 12. We have 10 already in terms of cumulative frequency. So when you add it to 12, it gives you 22. So we do that till we get to the last group, okay? So the last group actually should give you the total of all the frequencies, okay? So when we plot a cumulative frequency curve, this is what you see on your right. So it gives us from the 21 to 24 group, that is 3, okay? Then it goes on between 25 to 27, okay? The cumulative now becomes 10, okay? So it is marked accordingly, okay? And then, so when you mark all these points, then you join them with a line, then you get what I have here on the right. Okay, so that is a cumulative frequency curve. So it's another way of describing your qualitative data. Okay, now you will see on the axis that you have the median. We will talk more about it. That is the middlemost number. Okay, we have the lower quartile and then the upper quartile. Okay, we'll talk more about that very soon. Okay, any question about the cumulative frequency curve? Any questions about the cumulative?
I have a question.
Please go ahead.
Yeah. Please, in terms of the length, we are using figures there. Although we are working with quantitative data, does it mean if you use figures to represent the data?
Yes, it's you. I'm the only one who has not joined. You join me and you
Please, this is serious. I've told you, guys, I don't know how many times I should tell you to mute yourself. Okay?
Even praise, mute yourself.
Please, we have to be a bit more diligent. Okay, every time you should be checking whether, if you are not asking a question, just mute yourself because somebody was asking a question and you're also talking on the background. Okay, please. Okay, especially those of us who are using mobile phones. Okay, you can easily unmute yourself without even knowing. Please check it. Okay, other than that, the whole thing becomes very, very chaotic. Okay, please go ahead with your question.
Yes, so what I'm saying is that although we are the cumulative frequency test is used for qualitative data, we realize that the data we have
It's not
is
only qualitative data, but what I'm saying is that we can use one way of describing qualitative data is to use cumulative frequency curve. Is that okay?
Okay.
So it's not exclusively for qualitative data.
Alright, so the figures we have at the length, does it mean that if we use figures to represent the data and they want to analyze it? So that's why we got it.
Okay, so here the length, it could be in terms of how do you call it? It could be in terms of height or something. Okay, this is just an example. But this one, we are not using anything to you have specific groupings. Let's say you have you've measured something from 21 centimeters to 40 centimeters. Okay, so we are not using these numbers just to represent it. This is like a continuous grouping where we are putting groups into them. Okay, so we have 21 to 24. So this is not, this is an actual group or an actual length in your data set. So we are not using like 1, 2, 3 to represent something like married or married. Is that okay? I don't know whether I've answered your question.
Because we have the
You say because we have what?
qualitative and not quantitative.
I don't know whether I'm getting you. Because we are using qualitative. So you are saying that the 21 to 24 is not a number. Is that what you are saying?
Yes, so I said what I'm saying that the 21, 24, is it representing a qualitative data or is just a figure that's quantitative?
Yes, so it could be a qualitative data. That's why I'm saying that the qualitative cumulative frequency curve does not only, we don't use it to represent only qualitative data. It can be used to represent quantitative as well. But in this instance, okay, let's say you have different groups of people, okay, or like you could even have one group of people, and then you are checking the length, okay. All that you need to do is just count them, put them into groups, and then add them up as you go along, just to get your cumulative frequency, and that will enable you to plot your cumulative frequency curve. So whether it is you are using it for qualitative or quantitative data, okay, what we are saying is that cumulative frequency curve is one of the ways you can use in describing qualitative data.
Yes,
Is it okay? Hello?
yes, sir.
Please, is it okay? Okay, Nanama, please go ahead.
Yes, sir. I'm okay.
Okay.
Okay, thank you, sir. So does that mean the cumulative frequency curve can be used to represent both qualitative and quantitative?
Yes. But at this instance, we are just looking at qualitative data. Okay. Okay. Yeah, Nanama, another question? Okay. All right, so another way of describing this is is to use the frequency bar chart. Okay. So let's say we have figures related to how many times ice cream is sold. Okay. So if you realize for qualitative data, normally we deal with counts. Okay. So you see here the frequency, the one that we just did, the frequency, these are the counts. of the number of times a particular thing appears. Okay, here too is the same thing, just that we are representing them in a bar plot, okay, or a bar chart. So let's say week 1, we sold, for July, we sold 20, we counted 500 ice creams as compared to August, which was 800, okay? So in terms of count, you will see that week 1 is showing 500, and then for August is showing 800, okay? For week 2, the count is 800 and then 900 for July and then August, okay? And we do that for week 3 and then week 4, okay? So here, we are describing the qualitative data by counting the number of times something is sold, okay? So this one gives us the count, okay? And then we can represent this. So if you see your normal bar plot, okay, it represents the number of counts a particular observation is observed, okay, or happens. All right. Stephanie, yes. Stephanie, your hand is raised.
Hello, sir.
Yeah, please go ahead.
Okay, so please, you just explained that the qualitative data has to do with counts, but when we
Yes.
look at the types of quantitative data, we have discrete, and discrete also deals with counts.
Yes.
So what is the difference between counts under qualitative and counts under discrete, which is under quantitative data?
Okay. So let's go back to yeah. So let's say you have an ordinal data. Okay. All right. You've collected data on ordinal. So you have strongly agree, somewhat agree, neither agree or disagree. Okay. Now, first of all, this is an ordinal data, isn't it? Let's say if you have a data that is giving you the levels. Do you get me? Stephanie, do you follow?
Yes, please.
Okay. So let's say you have now collected your data and then you want to visualize it. Okay. Now you have 30 people say strongly agree, 20 people say somewhat disagree. Okay. 10 people say neither disagree or disagree. If you are visualizing them, then you use a bar plot to do it. So it's just counting the number of people who said they strongly disagree, the number of people who said somewhat disagree, and stuff like that. Okay. Now, when you come to discrete that is counted, it's also count anyway. But here we are not seeing any levels. Have you seen? So first of all, you need to consider the data type. If it is ordinal, it makes it an ordinal data. But within that, if you are visualizing it, you can count the number of times each thing appears and then visualize it as such. Is that okay?
Okay. Thank you.
All right. So we have the frequency bar chart here. Okay, so it can be used to count the number of occurrences. Okay, so this is one of the ways by which you can describe your qualitative data. Okay, so let's see this one. So we're going to have a class exercise. Okay. So a qualitative variable with 3 classes. So you have X, Y, Z. It's measured for each of 20 units randomly sampled from a target population. The data is as follows. So we have 20 samples, okay? Can you compute, so let's do the first one first. Compute the frequency of each of the 3 classes. So you have 3 classes. Can you compute the frequency of each of the classes? Please, all of you do it and then let me know the answer.
I've got the answer.
Okay, I'll be within a minute. Okay, so what is the frequency for each class?
X is 8.
X is 8, okay.
Y
Y
is
is
9.
9.
Okay.
Z is 3.
Z is 3. Okay, so compute the relative frequency for each of the classes. Compute the relative frequency. Remember, the relative frequency, we do it in terms of the percentage of the total. So do B, compute the relative frequency. If I can go back here. Remember, relative frequency. So remember, relative frequency is the frequency, class frequency over this, okay?
So now the relative frequency for X is 40%, Y 45%, and then Z 15%.
15%.
Okay, so they all add up to be 100, okay?
Yeah.
So if you want to display this in a pie chart, you can easily do that. Okay, so when you have time, display it in a pie chart and also in a frequency bar graph, okay? And then you can do it on your computer as well, and then see what the plot gives you, okay? All right. Let's talk about a histogram. Please, are we okay with this before we move on? We don't want to leave anybody behind. Are we okay with this, at least from A and B? Are we all okay with A and B?
Yes.
Okay. Anybody with an issue of calculating the relative frequency and also the frequency for each of the classes? Anybody? Okay. So you see that this was a qualitative data, okay? But we counted them. We counted them and we've been able to calculate the frequency for each class and also the relative frequency for each class, okay? So with that, we are able to display the results in a bar graph, or if we are using a pie chart, we can do that, okay? All right. So let's look at numerical data, some of the ways by which we can describe them, okay? So one of them is a histogram, okay? So here we're looking at, it's just like a bar graph, okay? Okay, that apply, but this one applies to numerical data. Okay, so you cannot use a histogram for qualitative data. It will not work. It has to be a numerical data. Okay, it has to be a numerical data. So the height of each bar of a histogram represents either the number of individuals in each group or the percentage of individuals in each group. That's the relative frequency of each group. Okay, so you will see that in a typical histogram, for each of the bar, okay, it's like the frequency, the number of times each observation appears. Okay, so for a bar between 400 and 800, we have only one. person appearing. Between 800 and 1,200, we have 1, 2, 3, 4. We have 4. Between 1,002 and then 1,600, we have 1, 2, 3, 4, 5. That is the highest. And then followed by between 1,006 and 2,000, that is 3. And then between 2,000 and 2,400 is 4. Now you realize something on the x-axis. Just pay close attention. On the x-axis, you see that the ticks, they are not in the middle of each bar. Okay, so you see that the bar is in between the numbers. All right, so it's not like 400 is showing here at the middle like that. No. So also between 400 and 800, the bar should be in between those ticks. Okay, so because that is the grouping. Okay, so between 800 and then 1,200, you see that the bar is between 800 and 1,200. It is not, the 800 line is not in the middle of the bar. Please, I don't know whether you are getting me. So when you are doing your histogram, be careful about, be mindful of the axis. Okay, the bars fall in between the figures. Okay, the figures are not in the middle of the bar. Please, do you follow? Okay, so this is a typical histogram. Okay, so the histogram deals with numerical data. You cannot use a histogram for a categorical data. Okay, so a categorical data can be represented by a bar chart, okay, and pie chart if you don't have any option, but try and represent it on a bar chart. Okay, all right. But for numerical data, we use histogram. One of the ways is a histogram. Do it. Okay. So another example of this. So let's say we have scores of a test. Okay, psychology test scores. Okay. So for the bar, we have the lower limit and then the upper limit. So that is the groupings. So between 39, let's say the between 39.5 to 49.5, the lower one is the lower limit. Okay, so between this 39.5 to 49.5, we have 3 observations within this group. Okay, we have 3 observations within this group. And then 49.5 to 59.5, we have 10 observations within this group. Okay, up to 159.5 and then 169.5, we have 1 observation in this group. Okay, so this can be represented on a histogram. Okay, so each of the bars shows the frequency. So here we can see that the highest group is basically the one for 79.5 and then 89.5. That is 147. It appears 147 times. Okay, all right. That's so between the lower limit of 79.5 and then 89.5, the class frequency is 147. So you see that on the histogram, it is the highest. Okay, so we can do this. So this one gives you the ranges. Now, supposing we change these groupings and then make it bigger, let's say from 39.5 to let's say 59.5. Okay, it will give us the groupings will become smaller. Okay, but when it becomes like that, you will not be able to see if there are some particular issues. So the smaller they are, the more you are able to see. You are able to see how the observations are distributed. Okay, let's say because this one we can just put all of them into 3 main groups. Okay, we could just do 39.5 to let's say 89.5, and then 89.5 to let's say 139.5, and then 139.5 to 169.5. So we are just going to have 3 bins. Okay. With that, you will not be able to see how, though it gives you the groupings, all right, but you will not be able to see how these numbers are distributed. Okay. So as much as possible, you don't want to have so many bins. On the other hand, too, you don't want to have very few bins that you are not able to see how the data is distributed. So you need to balance it. Okay. So now we have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 bins, okay, or 13 groupings. Okay, so we are able to see how this data is distributed. Okay, so that means that those with a score of 79.9 and 89.5, okay, are the largest group of people. Okay, followed by 89.5, then 99.5, and so forth. Okay. So basically, this is what we call a bell-shaped curve. Okay, it's like a bell. Okay, that is, the data is kind of normally distributed. Okay, it starts and then it rises up and then begins to fall. Okay, and then they are spread out evenly. So it's like a bell-shaped curve. Okay. Any questions on the histogram? Any questions on the histogram? Yes, Bernard. Bernard, we are listening to you. Bernard, go ahead with your question.
Okay, Nana, please, can you hear me?
Yes, I can hear you. Please go ahead with your question.
Okay, I'm looking at the 2 examples we just did under the histogram. The first graph, we have spaces in between the bars, and the second one we don't. So I want to know the difference, since that's one of the differences between a bar graph and a histogram.
Okay. All right. So basically, with that's a good question. Basically, with a histogram, it's like this. The way these ones are cluttered together, like this. The first one was just to show you that the histogram has the number of observations in there. Okay. The number of observations that you have in each group. Okay, but remember that in a way, it's just like a bar chart. Okay, it's just like a bar chart, but with bin ranges. Okay, so this one was just to show you that for each of the bars. Okay, so this is a simplified one. This is a simplified one for you to know that each of the bars has frequency in there. Okay, but a typical histogram will be something like this. Okay.
So could it also be that, looking at the first graph you showed us, this one, the base, that's the length, the bars are in between 2 numbers, whereas with a bar graph, we write the number under one bar. I don't know if that can also be a difference between this one and the normal bar graph.
Okay, so with a normal bar graph, remember that it is the normal bar graph deals normally with counts. Okay, it is not a numerical data.
Okay.
All right. So that is the main difference between the histogram and then the normal bar chart.
Okay.
Okay.
Thank you.
So let's see. So let's look at the mean. Let's look at the mean. So the mean of the variable x, okay, normally with this, we call it x bar, okay? It's calculated by adding up all the values in a data set x and then divided by the number of values in that data set. Okay. So if you take a typical data set, let's say from 5, we have this 5, these are the number of observations, 5, 3, 8, 6, 8, 5, 6, okay? So what we are doing is that we take the first number, okay, up to the 5th number, okay? So that's the number of observations in the data set. So we add 5, 3, 8, 5, 6, okay? And then we divide it by the total number of observations, that is n, okay? That gives you 5.4, okay? So basically, that is how a mean is calculated, all right? Can we try this one, okay? Forget about the double, I think. Yeah, let me remove this double. So can we try X? Let's try X and determine the mean. Okay, so you add, what you do is that you add everything in the data set and then you divide by the number of observations. Okay, can we all do it? Can we all do it? I know calculating the mean is easy for all of us, but let's just do it and then see the answer. What does the answer give us? What? 40. 40. Did we all get 40? Are you sure it's 40?
2.7.
2.7. Okay, did we all get 2. So we have two answers now. We have 40 and 2.7.
2.7.
2.7. What did you get?
2.7.
Okay, all right. So we added everything in the data set and then we divided by the number of observations. Okay. Okay, let's try the second one.
The second one is 40.
The second one is 40. Okay. Oh, probably it was the second one you were referring to.
Yes.
Okay. Did we all get 40?
Yeah, 40.
Yes, 40.
Okay, all right. Okay, so that means that when it comes to me, we are all gurus. Okay, Nanama, yes. Nana, go ahead.
Okay, the number of observations. Oh, okay. I get it now.
You get it now. Okay, all right. Okay, so you count the number of observations and then you divide it by the total number. Okay, so the total number in the data set will be your numerator. Okay, and the number of observations will be your denominator. You divide and then you get it. Okay. Okay, now your hand is still up. Do you have a second question or you are okay? All right, good. Please, are we okay with the mean? Are we okay with the mean?
Yes, please.
Okay. Let's check the median. So the median is the middlemost value or the middlemost number in a set. Okay. So how do we go about determining the median? First of all, you need to sort out your set sequentially from the highest to the lowest. Sorry, or from the lowest to the highest, whichever. Okay. So from the lowest to the highest. All right. When you sort it out, then you can count the number of observations. The one in the middle is your median. So let's say we have 10, 14, 2, 68, 99, 85, and 1. Okay. So what we have to do is to arrange them sequentially from the lowest to the highest. Okay, so now we have arranged them to be 1, 2, 10, 14, 68, 85, 99. So how many points do we have? We have 7, isn't it? 1, 2, 3, 4, 5, 6, 7. So we have 7 numbers. So the middlemost number, okay, will be what? 14, isn't it? because we have the first 3 and then the last 3. So the middlemost number is the 14. So 14 is the median. Okay. So with this in mind, try X, okay, and then determine the median. Try what we have here and then determine the median. Now, are you asking a question?
Yes, please.
Okay.
What if you get 2 numbers as the median?
Okay, so we'll get there. So if you get 2 numbers as the median, that means that you need to add them up and then divide by 2. Okay. You take the 2 middlemost numbers and then add them up and then divide by 2. That will give you your. Okay, so work it. I'll be with you.
41. 41.
41. Okay. Let the others work it out. I'll be with you in a minute. Okay. What answers are we getting?
41.
41. Did we all get 41? Please, did we all get 41? Anybody got a different answer? Okay, so one of us should take us through. How did you calculate it? Any volunteer?
Yeah.
Okay, please go ahead.
Numbers in order.
Okay.
And yes, the total number was 8.
Okay.
Meaning I have 2 middle numbers. So the middle number is 14 and 68, which I divided by 2.
Okay.
So 14 is 82 divided by 2 will give.
Okay, excellent. Excellent. Okay. All right. Good. So let's look at the mode. Okay. Mode. So mode is the most common number in the data set. Okay. So the mode of following data set. So you have 1, 2, 5, 5, 6, 3. Okay. So here the most common number will be 5, isn't it? Because it appears twice. Okay. So data set with one mode normally is called a unimodal data set. Okay. You could have a bimodal data set where the modes are, so you have 2 peaks in there. All right. So you have 2, here we have 2 and then 3, or multimodal. All right. So those are the ones you should. So now we have the mean, we have the median, we have the mode and stuff like that. So what we need to do, we remember when we were dealing with missing values, when we were doing our exploratory data analysis, do you remember? We removed the missing values, okay? We remove the missing values. Now, you have to decide when you have a data, okay? If you have outliers, okay, you might decide to, you have to decide, for instance, if there are missing values, do you remove them or do you replace it with the mean, or you replace it with the median and so forth, okay? So that will also depend upon the structure of your data, okay? The way the data is structured. That will also help you to determine whether we are to use the mean or we are to use the median. Okay, so let's see how this in situation, let's see different situations where it will be good to use your mean or it will be good to use your median. Okay, so where you have symmetrical data, for instance, so one mirrors the other. Okay, in such instances, you see that the mean and the median are very close to each other. Okay, so since the mean is more sensitive to extreme value, it works better for symmetrical data. So if you have symmetrical data, okay, or a data that is normally distributed, okay, then the mean is best to use as your measure of your center. Or as the measure of your center, the mean is best to use when you have symmetrical data. What about if you don't have symmetrical data? What happens? Okay, so let's say we have a left-skewed data. Normally, when we say a data is left-skewed, it means that it has a long tail to the left. So you see that most of the data will be to the left, okay? And then just some small part will be to the right. So here, a typical, so if you do your histogram, and then it's giving you something like this, for instance, then it should tell you that this is a left-skewed data. Okay? This is a left-skewed data. So the purpose of, for instance, doing a histogram is not really just for them to see that you know how to do a histogram, no, but it gives you an idea as to the structure of the data, okay? So a typical, so this one, a typical histogram like this is bell-shaped, okay? So this is symmetrical, it mirrors each other. So the mean will be the best measure of center to use. If it's asymmetrical or it is left-skewed, okay, it has a long tail to the left. So use that to remember left-skewed data. It has a long tail to the left, okay? And because it has a long tail to the left, okay, most of the data is drawn to the left. And because mean is sensitive to, extreme values, it draws the mean to the left, okay? So here you see that the mean is drawn to the left. So in such instances, the median will give you a greater consistency. Okay, so in such instances, it's better to use your median as your measure of center rather than the mean. Okay, so a left skewed distribution, also called negative skewed distribution, has a long tail to the left. Okay, so when it is like that, when it is skewed, the mean and the median are different. The mean is pulled in the direction of the skew, so it is lower than the median on the left skewed data. Okay, all right. Higher than the median on the right skew data, okay, because the mean is pulled to the right. So we'll talk about right skew data. Any questions about the left skew data? Okay, it pulls everything. So it has a long tail to the left. Okay, so most of the data are drawn to the left. And because most of the data are to the left, it draws the mean also to the left. Okay, it draws the mean to the left. So in such instances, it's better to use your median as your measure of center. All right. Any question? Any question? Okay, let's look at right skew data. So here too, the same principle, okay, with right skew data, okay, it draws most of it has a long tail to the right, okay? It has a long tail to the right. So your histogram will depict something like this, okay? And because it has a long tail to the right, most of the figures are to the right. Therefore, it pulls the mean also to the right. So in such instances, the mean, when you have a right skew data, the mean will be greater than the median, okay? Well, the mean will be greater than the median. So when you have a right skew data or a left skew data, it's better to use your median, okay? Because the mean have been affected by the values. Okay, it's been affected by the values either to the right or to the left. So when you have a skewed data, do well to use your median as your measure of center instead of the mean. Okay. Any questions about the right skewed data or the left skewed data? Any question?
I have a question.
Yes, please go ahead.
I'm not so clear about what the measure of center means in this context.
Okay. So the measure of center basically means that you see it helps you to put everything into, remember when we're doing clustering, okay, the measure of center was the clusteroid. Do you remember? Okay.
Yes, please.
So most of the data was centered around that measure of center. Okay. So knowing the measure of center is important. Okay. However, determining the measure of center depends upon the structure of your data. Okay, so here we are seeing that if the data is symmetrical, that is, if it is a normal distributed data, okay, that's what we call is symmetrical. Okay, if it is like this, then both the mean and the median, they are very close to each other. So normally we use the median, we use the mean if it is symmetrical. Okay. If it is symmetrical like this, if it is normally distributed, then the mean is what we use as the measure of center. All right. Okay. Now, when it is not like that, if it is skewed to the left or it is skewed to the right, if you use the mean as the measure of center, it might give you wrong information. Have you seen? It might give you a distorted view of the data. So in such instances, we use the median as the measure of center. All right. So in such instances, if you have a left skewed data, okay, and then you want to calculate the measure of center, we use the median instead of the mean. Okay. Okay, so in terms of averages, use the median instead of the mean. All right. Let's look at the spread of data. So we've looked at the measure of center. Let's look at the spread of data. The spread of data. The spread of data. So it describes how spread apart or close together data points are. So you see the first diagram, they are very compact together, okay? So here they are very close to each other. However, the second diagram on your right, you see that it is much more spread apart, okay?
Anna?
Yes.
Right, so thinking about the skewness of the distribution.
Oh, you want us to go back?
Yes, please. Yeah. Center.
Please
All right. So unless maybe we are just measuring the center and that's it. But for a typical example, if you are measuring performance and let's say the performance of a class and we put it in a normal distribution, okay, we will have to use the mean or the average instead of the median, because the median would just be the center number, right? But the mean is actually calculated, and then it will help you know whether the class is overperforming or underperforming, right? So in that case, you will have to use the mean.
Yeah.
Okay.
The point we are making here is that what you are saying is not wrong. The point we are making here is that let's use the same class performance. Okay. Most of the people got, let's say, 10%. Okay. And then somebody scored 90%. All right. So if you want to calculate the mean, you will say that is the performance is good because it is 50%. We add the 10 and then the 90, the performance is good.
Right.
But in actual fact, it is not good. The extreme value of the 90% has affected the actual performance of the class, which is 10%. Have you seen?
Yeah.
So because we have extreme values, okay, or in this case, let me say outliers. Outliers can affect how you describe your data, the conclusions that you draw. Okay, so in order to avoid that, why don't you concentrate on the ones in the middle? That is the median. So that is the main point. So as for the mean, you can calculate it. But where you do not have outliers or extreme values, then this is fine, like what we have here. Then the mean is fine. But where it becomes left skewed or right skewed, that means that we have some extreme values in there. And if you don't take time and then you go and use the mean, it will give you a distorted conclusion because of the extreme values.
Extreme values. Okay.
Okay.
But so in this case, like the left skewed, right? We can interpret this as maybe using the average. So we see this is the average performance.
Yeah, so you say, so you talk about the median performance.
Oh, okay.
Okay.
So once there's a skew, left or right skew,
use the median.
Talk about the median.
Yes, talk about the median. Use the median. That gives you, at least it gives you, it is not distorted by extreme figures. So the mean is the ones in the middle, have you seen? So it is not distorted by extreme figures, either to the right or to the left. Yeah?
Okay.
Good. So let's look at the spread. Let's look at the spread. I'm watching the time. When do we go for break? Let's finish this.
10 o'clock.
10 o'clock, good. Okay, let's finish the variance and then the standard deviation, and then we'll go for our break. Okay. So the spread tells us how the variability in our data. Okay, so you see that the first diagram, okay, is very close to each other, very compact, whilst the other one is spread, okay, a bit more varied. So let's look at the variance, how we calculate the variance. Okay, so the variance measures the average distance from each data point to the data's mean. So let's say you have mean, okay? You have quiet. Hello. Please mute yourself. Okay. All right. So you have the variance. Okay. So in order to calculate the variance, I think we did this the last time when we were calculating the Euclidean distance. Okay. So you have the mean and then the distance from the mean. Okay, so when you calculate the distance from the mean, so it's the distance between the actual data point and then the mean. All right, then we look at the squared differences. We add all them up. Okay, so if you look at here, for instance, value 3, okay, is the distance between it and then the mean. Okay, if you look at value 1, is the distance between it, you see the arrow from 1 to the mean. If you look at the data point at the top, okay, of 1, okay, is the distance between that and then the mean. Okay, let's come to the right side of the mean, that is value 4. The data points is the distance between that and then the mean. Okay, so when you find the differences between the data points and then the mean, then we square them up. Okay, we square the differences. When you square the differences, then whether it is negative or positive, it doesn't matter, okay? Everything becomes squared, so everything becomes positive, all right? Then when we've done that, okay, we add all of them up, okay? And then we divide by the sum of squared distances, okay, by the number of data points, okay? So to calculate the variance, we start by calculating the distance between each point and then the mean. So we get one number for each data point. Is that okay? We then square each distance and then add them all together, okay? Finally, we divide the sum of squared distances by the number of data points, okay? So the higher the variance, the more spread out the data is, okay? And then the smaller the variance, the more compact it is, okay? So let's look at the mathematical formula. Okay. So as for the mean, we've seen how the mean is calculated, okay? We've seen how the mean is calculated, right? And then we have the, yes.
Nana, please, can you go back one slide?
Yeah.
Another slide.
Okay. Yeah.
Hey, another one.
Hey, why didn't you ask your question then?
I was thinking.
Okay. All right. Okay. Are we okay here?
Yes. Please, what did you say about here? I was too processing.
So yeah, we just have two diagrams, one on the left, one on the right. Okay. So you see that the one on the left is a bit more compact. It is not spread out like the one that is on the right.
Mm.
Okay. So we are just looking at the measures of spread, how you can measure the spread of your data.
Okay.
And the main measures of spread are variances and then standard deviation. In fact, the standard deviation is the square root of variance. That's all. Okay.
Okay.
All
so
right.
one of the applications here or the interpretation here is like, so
how
again,
spread your data is. Yes.
Yes.
Okay.
Again, using maybe class performance, right? So here
Class
you can say
performance.
that.
Okay. So if we are comparing two classes, okay,
Yes.
and then the standard deviation of one class performance is, let's say, 1, and then the standard deviation of another class performance is 2. Okay. So you see that the one with the 2, that means that it is much more, there's further away from the class performance of the one that was 1. Okay, so the one that was 1 is nearer to the mean performance than the one that is 2.
That is 2.
Standard deviations, okay.
Yeah.
All right, good. So let's look at the population variance here, represented by rho. Okay. Right, so we have, so the population variance is the average of the square deviations from the mean, okay? All right. So the square of the values distance from the distributions mean. That is, you take the value that is x1 and then deduct the mu, that is the mean, okay? And then you square the difference, okay? So you see that what is here is what is summed up here. So we take the summation of it, we take the summation of all the squared means, and then we divide by the number of observations, that is 1 over n. So 1 over n is the number of observations. Okay, so n basically is the number of observations, but we divide it by the total square differences. That's why here is 1 over n. Okay, and here we are taking the whole population. That's why we have capital N. Okay, I will explain later. Where we are taking a sample, then we use small n. All right. So basically, the population.
Hello, Nana.
Yes.
Mental here again. So all these formulas and computations, do we need to Papa, or because you'll be using we'll be computing it, we don't need to.
So know how to use it.
Okay, so we just know how to use it.
Don't
right?
worry,
Because
we'll be doing a lot of exercises. So
okay.
So this is the formula, okay? But we will go and calculate everything and come and put it in the formula. You understand it even better. All right. So we have population mean, and then we have, so if you are taking the mean of the whole population, let's say that we want to look at the performance of business analytics class, okay? Then the whole population, let's say if we are about 60, then the whole population is the 60, okay? In that case, we use the population mean, okay? And then the population, if you want to look at the spread, we use the population variance because we are using the whole population, all right? Okay. Now, if we want to look at the performance of students in KNUST, and then we are just sampling students from, let's say, business analytics class, then it is not the whole population. Then that becomes the sample. Okay, so we'll discuss that. So, but this is talking about the whole population. Where it is a sample, the formula is the same, but just that here the n is small n. Okay, and then the sample variance is n minus 1. But everything stays the same. Okay, all right, everything stays the same. So the sample mean serves as an estimate for the population mean. That is the mean. So when we don't know the population mean, we'll do more when we are looking at sample distribution and stuff like that. Okay, when we want to estimate the population mean, we don't know, then we take a sample. All right. So here the variance is still the square differences, the summation of the square differences between the means and then the observations, okay, divided by the number of observations, that's n minus 1. All right. Okay. Any question about the sample variance, and then we'll go on to the standard deviation, and then we take a question and then work it out. Now, when we come to the standard deviation, it's the same, it's just the square root. It's just the square root. Please, are you asking a question? Okay. Please, I can't see the person, so inform the person to me. Okay. All right. Right, so standard deviation. So the standard deviation is just the square root of the variance, okay? So if it is a population, we are looking at the whole population, then it's the one on the left, the one with the big N. However, if it's a sample, okay, and we're looking at the standard deviation, okay, we just take a square root of the variance. Remember, everything in the square root is the variance. Okay, when you add the square root to it, then it becomes the standard deviation. Okay, so let's see this example. To calculate the sample variance and standard deviation of this data set, 2, 3, 3, 3, 4. Okay, so now we have, so this X is represented by 2, 3, 3, 4, the first column. Okay, 2, 3, 3, 3, 4. Now the summation of that gives us 15, right? Now, for us to determine the mean of this population, we have 15. How many observations do we have? 5, isn't it? So if we divide 15 by 5, that gives us a mean of 3, is it not? Okay. So what we want to do is to calculate the summation of the square differences between the data points and then the mean. Now we have calculated the mean to be 3, and then the data points we have 2, 3, 3, 3, 4. All right. So to look at the differences between the first data point and then the mean is 2 minus 1. Okay, that is, you have X minus X bar. 2 minus 3, sorry. 3 being the mean. And then it gives us negative 1. Okay. This negative 1, we are not interested in negative 1. We are not interested in the difference. We are interested in the square difference. So when we square negative 1, it gives us 1 on the last column. Okay. Now let's go to the second row. Our data point is 3. Our mean is 3. Therefore, the difference is 0. So When you do a square of that, it also gives you 0. Okay? Our third data point is 3. Our mean is 3. Difference 0. Square difference also 0. We do up to the 5th one, that is 4 and 3. The data point is 4. The S bar is 3. Okay, so X minus X bar gives us 1. Okay, we are not interested in the difference. We are interested in the square difference. So when we square 1, it gives us 1. Okay, so when you add all of this, it gives you 2. Okay, and then we divide by the number of observations, n minus 1. So the n is 5, 5 observations minus 1. That's what we have in the variance here. So the variance here is 2 divided by x, 2 divided by 5 minus 1. That gives you 0.5. That is the variance. Now, if you want to calculate the standard deviation, we just find the square root of the variance. So if the square root of 0.5, then the standard deviation square root will be square root of 0.5. That gives us 0.707. Okay. Any questions on this one? Any questions on this one?
Yes, Nana.
Yes.
With the concept of population and sample,
Yeah.
I wanted to get the understanding well. So normally, the population is the full number of
The
entities you
population
have.
is the whole population. So if you wanted to find student performance of KNUST students, then we take, or we want to find the views of KNUST students on something on campus. Then we interview all the students of KNUST, and then we take their views into consideration. Okay. However, practically, sometimes it's difficult to get the whole population. Let's say you want to find something about the people who have cancer. You cannot go to all the hospitals in Ghana to get that information. Is that not it? So normally what we do is that we take a sample, and then with the sample, we do an estimation. Okay. So the larger the sample, we will see that next week. The larger the sample, okay, the better your mean will be closer to the population mean. So if you want the whole population mean, if you calculate, let's assume that we take the whole of KNUST, okay, about, let's say, the ages of all the students in KNUST, and then we find the mean. That will be the population mean, isn't it? Hello?
Yeah. Yes, sir.
But if for some reason we are not able to take all sample, interview all the students in KNUST, we just take a sample of the students. Okay, let's say we take 60% of the students. Okay, we sample 60% of the students, and then we find the population. We find the mean. Okay. Now, if we take 60% of the students and find the mean, and then as compared to taking 80% of the students and finding the mean, you will realize that the one that has many students, its mean will be closer to the whole population mean, wouldn't it? Of 100%.
Yeah.
So the larger your sample size, the more closer your mean is to the population mean. All right. So that is why normally in quantitative studies, we want a larger sample size. Because the larger the sample size, then you are getting closer to the population mean. All right.
Okay. So Nana, with the formula, I know that the sample formula says it should be divided by the total sample number. That's n minus 1. Why the minus 1? Why wasn't it like minus? Is there
yes,
an
because
explanation
it's
to
an
that?
estimate. Because it's an estimate.
Okay.
Okay.
Oh, okay.
Because it's an estimate. So that's why we do S minus 1. N minus 1. Okay.
Thank you.
All right. Okay, so let's do another one. This time around, Let me see if I can get some space here. Okay. Let me copy this. So let's change this to 5, 3, 6, 8. Okay, all of us, let's calculate the variance and then the standard deviation for the second one. So you can watch what I've done here. Okay, so let's do for the second one. Calculate the sample and standard deviation. Okay, for 5, 3, 6, 3, 8. This one, work it, or don't use your laptop to do it, because in the exams, you will not be using your laptop.
Hey, dog, we'll be using the machine.
No.
Now I
These calculations in exams.
So work it, manually, okay?
But Nana, why won't you be using computers at the exams?
Because you'll not be using computers in the exam room.
But Nana, the job will be using computers to do it too.
Yeah, so by that time you know what goes into it. You know the what do you call it? You know the reason why things are done. So you are being trained. You are on the training field now.
So
Nana, that is for BSc. It's for BSc.
Okay, so you use laptop to do it when you get to the exams.
And if you are supposed to learn how we are going to use it there, then you're supposed to ask us theory questions, not calculation.
Don't worry, we have not gotten to where the exam is. So you calculate what I'm giving you. Calculate what I'm giving you.
And we are trying to argue it so that maybe the exams will change.
The exams questions have already been set.
Hey,
Boko.
hey, we back.
Okay, so just put them in a table, just follow it. When you follow it, it's difficult to get it wrong. So just create a column for X, and then a column for your mean, that's your X bar. The third column should be the differences. The fourth column should be the square differences. When you finish, just add them up. The summation of your square differences is your variance. That's all. And when you finish, just find the standard deviation of the variance. Easy. Yeah, anybody done?
Variance is 4.5. Variance is 4.5.
Okay, just a minute. Let me just create something here. Okay, so the variance is what? 4.5?
Yes.
Okay, and then the standard deviation.
2.1.
2.1. Please, anybody with a different answer?
Hello. No.
Yes.
I had the variance, like I had 4.75 for the variance.
So you have 4.75
Yes, please.
for the variance. Okay, and then the standard deviation.
2.3.
2.3. Okay, any other?
No.
Then we all work it together.
No.
Anybody with a different figure? Please, the ladies, I'm not hearing from you.
Hello, please, Anna.
Yes.
My standard deviation is 2.1 instead 2.1, not 2.3.
Okay, all right. But your variance is 4.45. 75. Okay. Please, any other? Any other? Any other? Okay. Let me see if I can replicate this here.
I also got something different. I also have 3.6 for the variance.
Yeah, 3.6
and
for
1.867 for the standard deviation.
Okay.
That's
Let me just. Probably I need to create the tables here.
You can copy the whole table and just instead of copying the text.
Yeah, I'm trying to copy it and it's not working.
I just make a duplicate of the slide.
Okay.
Okay, so can you give me the x is 5, 3, 6, 3, 8, yeah? So we have we have 5, 3, 6, 3, 8. Okay, so what is our mean? When we add all this, what do we get? That's 5 plus 3, 8.
25.
25, okay? So we have the summation of all this to be 25. Okay, so since we have 5 observations, the mean will be 25 divided by 5, isn't it? So our S bar is 5. Okay, so this will be 5, this will be 5. This will be 5, this will be 5. Okay, so what is the difference? So 5 minus 5 here will be 0.
Yes, sir.
5 minus 3, 3 minus 6, that will be negative 2, yeah? And then 6 minus 5 will be 1.
1.
And then 3 minus 5, negative 2.
Negative 2.
Okay, and then 8 minus 5 will be 3.
3, yes, sir.
So let's look at the square differences. So the square difference, so the square of 0 is 0.
0.
The square of negative 2 is 4, isn't it? Negative 2 times negative 2 is 4, positive 4. The square of 1 is 1. The square of negative 2 is what? 4. And then the square of 3 is 9, isn't it? So what is our variance? Let's add everything. The square difference. 5, 9, 18, isn't it?
Yeah, yes, it's 18.
So we have here 18. So the number of observations is 5. So it's 5. N minus 1 is 5 minus 1. Okay. So that should give us what? 18 divided by 4 is what? 4.5. 4.5. 18 divided by 4. 4.5. So the square root of 4.5 is what?
2.12.
2.12. Okay. So that is the standard deviation. Please, are we all clear? So this is 5, 3, 6, and then 8. Please, are we all clear on this one? Any questions on what we've just done? So we've looked at the variance as well as the standard deviation. Any question on what we've just done?
Please, the standard deviation is 0.2.1.
Okay, is the old one. So the standard the square root of 4.5 is what? Can you give it to me again?
2.12.
2.12. Okay.
Nana, please, and the mean too is 25 over 5 plus 5.
The mean, yeah, okay. Thank you. Please, any question? So you see that it's not really difficult. Okay. Please, any question on this? Any question on this?
Nana, the mean 25 divided by 5 is 5, not
It's
3.
5, yeah. Are we okay?
Yep.
Okay. So let's
I
go
want to
for
find out in an exam setting. In an exam setting, you need to put the formula before you say calculation.
You say?
I want to find out in an exam setting, you need to put the formula before you.
Oh, yes. So you code the formula and then you go and put everything in the front. That's the first thing you do. Okay. So just quote the formula. Okay. All right. All right. Okay. So let's go for a break. We come back 10:35. Okay. And then we continue.
Okay.
Let's see the
Hello, sir.
Yes. Are you ready
I'm
now?
back. Yes, thank you.
Okay. All right. All right, guys. Okay, let's continue. So let's look at other aspects of measures of spread. Let's look at percentiles. Okay. Sometimes you want to report based upon relative standing. Okay. And one of the best way to do that is to use percentile. Okay, so a percentile is a percentage of individuals in a data set who are below where a particular number is located. So for example, when we say 90th percentile, okay, it means that if it's an exam, okay, and your score is at the 90th percentile, it means that 90%
serious
of the students are below the score that you got.
Yes, you know, to the extent in
Mpache yo, say ebiawa oba ne be fe.
So if your exam score is at the 90th percentile, for example, that means that 90% of the people taking the exam will you score lower than you did, which invariably also means that 10% scored higher than you did. Okay. So let's look at how we calculate the percentile. Now, these steps I'm going to tell you might not make sense now. Don't worry, we will take practical example. It will be clearer. But let me go through it. Okay. So first of all, there are 4 basic steps. So first of all, you order all the numbers in the data from the smallest to the largest. Okay. Then you multiply your K. Please, guys.
I have a question.
Oh, wait till let me go finish.
Okay.
All right. Okay, you ask your question. Please, when you want to ask a question, raise up your hand. Then everything is organized instead of just.
Okay.
Right.
Sorry.
Yeah, please go ahead.
I was saying, we kind of missed you when you were explaining the percentile. So it wasn't so clear.
Okay, let me go back. So with regards to the percentile, sometimes you want to give a report based upon relative standing. Okay. So the main thing about percentile is that it gives you information about relative standing. Okay. So if you are taking an exam and then we say that your mark is at the 70th percentile, okay, it means that 70% of the people who took whatever marks you got, okay, if it's at the 70th percentile, that means that 70% of the people got a lower mark than you got, okay? So if we say that you have your score is at the 90th percentile, it means that 90% of the people taking the exam with you score lower than you did. If it's at the 95th percentile, it means that 95% of the people scored lower than you did, and also 5% scored higher than you did. All right? Is it better?
Yes, please. Thank you.
All right. So let's look at the steps you can take in order to determine a percentile. Okay. First of all, you will need to order your numbers in the data set, okay, from the smallest to the largest. Okay. Multiply your K% times the number of observations in your N. Okay. Now, after doing that, if your results in step 2 is a whole number, then you go to step 4. Okay. If your results is not a whole number, then you need to round it up to the nearest whole number and go to step 3B. Okay. All right. So if it is a whole number, then let's go to step 4. Then count the numbers in your data set from left to right until you read that whole number. Okay. The K percentile is the average of that corresponding number in your data set and the next number in your data set. So that means that you add, just like we did for the median when it was an even number, you add here, if you calculate and it's a whole number, you add the 2 numbers and then you use that in doing your calculation. However, if your number is, you count 3B, if your number is in the data set is not a whole number, okay, then you count the numbers in the data set from left to right until you read the value from step 3A, all right? The corresponding number in the data set is your K percentile, okay? So let's take a typical example. This will make much more sense. So let's say we have test scores for 25 people, okay? in order from the lowest to the highest. So this has been ordered already. So from 43%, okay, to 99%. So this for 25 people. First of all, we want to calculate the 90th percentile, and then we come back to do 20th percentile. So 90th percentile, first of all, you find 90% of the number of scores. Okay, so the number of scores here, so we are doing step 2, okay? Multiply k percent times the total number of numbers n. Okay, so the number of scores here is 25, and we want to calculate the 90th percentile. So we multiply 90 times 25. That gives us 22.5, okay? Now, since this is not a whole number, so we run it up to the nearest whole number. So yeah, you run it up if it is not a whole number, we run it up to 23. Remember, even if it is 22.1, since it's not a whole number, run it up to 23. Okay, it's not only when it is more than 0.5 or so far as it is not a whole number, just run it up to the nearest whole number. Okay, all right, so this is not a whole number, so let's run it up to the nearest whole number. So that would be 23. So we go to step 3b. Okay, so we count our numbers from left to right, okay, until we get to the 23rd number in the data set. So when we go to the data set that we had here, the 23rd number, remember it's up to 25. So the 23rd number is 98. All right. So it's 90 times 25. That gives us 22.5. Because it's not a whole number, we rounded it up to 23. So 23 is the number, the 23rd number in our ordered data set. Okay, so the 23rd number is 98. Okay, so the number 98. So this is our 90th percentile for this data set. That means that at a score of 98, 90% of the students got more less than 98%. Okay, so that means the person who got 98, okay, 10% of the students got more than 98. Okay, and then 90% of the students got less than 98. Any questions about the percentile? Will I go over it? So if it is not a whole number, round it up to the nearest whole number and then count to the number that you got. That will be your percentile. Okay, so let's see for percentile, the 20th percentile. Now, it's still the same process. So we've ordered them. So let's say step 1 is done already. We've ordered the numbers. And because it's 25 observations, we'll multiply it by 20. Okay, so if we multiply it by 20, what you get is 5. This is a whole number. Okay, Solomon, I'll get back to you. Okay, just a minute. This is a whole number. So what you do is that we go to step 4. And what is step 4? The 20th percentile is the average of the 5th and then the 6th. So you go to step 4 and then you take the 5th and then the 6th. You add them up and find the average. So if it is a whole number, here the number was 5. So let's count to 5. 1, 2, 3, 4, 5. That is 62. So you take the 5th and then the 6th, and then you add them up and find the average. That is 62 plus 66. You find the average. So when you find the average, okay, 62 plus 66 gives you the average, okay, of 64. So the 20th percentile of the data set is 64, okay, meaning that 20% of the students scored below 64. Okay, Solomon, your hand was up. Were you asking a question? Or you are okay? Somebody's hand was up. Was it Solomon? Or you are okay? Yeah, Delasi, please go ahead. Delasi, we can't hear you.
Hello.
Yes, Delasi, please go ahead.
Can you kindly take us to the slide which gives us the formula for the percentiles? I wasn't really clear on the
Following. Okay, yeah,
difference.
let's go through it. Is this one? So first of all, you order the numbers from the smallest to the largest, okay? And then whatever percentile you are looking for, just multiply it by the number n, or the number of observation, okay? Now, between 3 and 8, where your result is a whole number, then round it up. Where your result is not a whole number, okay, round it up to the nearest whole number, okay? So when you round it up to your nearest whole number, that will be your percentile figure you're looking for, all right? Now, where the result is not a whole, it's a whole number. Where the result is a whole number, let's say you multiply, we are checking for the 20th percentile. We multiply it by 25, we get, I think we got 5, okay? So 5, because it's a whole number, count to the 5th number. When you count to the 5th number, add it to the 6th number and find the average of it. That would be your percentile you're looking for. Okay. All right. So let's work out for 70th percentile. Please try it and then let's see. Work out for 70th percentile. Or work out for the 75th percentile. Work out for 75th percentile. Work out for 75th percentile. Yes, the last thing.
Please, I got 89.
You got 89. Okay. Okay, so let's whilst we are waiting for the others, work out the 25th percentile. Okay. So we are working for the 75th percentile and then the 25th percentile. Yes, the last one.
Please, I actually have a question.
Okay.
So, rounding it up to the nearest whole number, it's one is below 0.5.
No. It's not. This is not about 0.5. I explained this. So far as soon as you work it and it's not a whole number, just round it up, whether it's below 0.5 or not.
Okay, sure.
Okay. So as soon as it's not a whole number, just round it up to the nearest whole number and then work with it.
Okay, then I got 68.
You got 68 for the 25th percentile. Okay. All right, Ernest.
Please, I was going to give you an answer. It's the same answer.
Okay. All right.
So 68.
Okay.
Yeah.
Okay. Any other question? The last, your hand is still up. Please, did you all get the same thing? 75th percentile and then the 85th percentile. So the 75th percentile was 89, and then the so the last, can you take us through how you calculated the 75th percentile? And then another person will take us through the 25th percentile.
Yes, please. Okay, the 75th percentile, I multiplied 0.75 by 25. 0.75 is basically 5%. So after doing that, the result was then rounded up because I got a decimal. I got
So tell us the
18.7.
figure that you got. You go out. Tell us everything.
18.75.
Okay.
So I rounded it up to 19.
Okay.
Yes, please. And then the 19th figure is 89.
The 19th figure is 89. Okay. Good.
Classmates are 75th percentile.
Okay, good. What about the one who calculated the 25th percentile? Can somebody take us through that, apart from the last year? Yes, Christiana.
I multiplied 25 over 100 and 25% by 25, and I had 6.25, and I ran it to 7. And when I counted it, I had 68.
Okay, good. All right. Okay. Excellent. Okay, so you know how it's done now, all right? So if it is Christian, if you can put your hand down. So if it is a whole number, you just count and then take whatever you calculated and then add the next number, find the average. However, if it is not a whole number, it is a decimal, just run it up to the whole number, and then that is your percentile. Okay, and then the meaning of the percentile is that whatever figure you have, okay, that means that that score that you had, if it is 20th percentile, that means that 20% of whatever data you are looking at is below the value that you've calculated. Okay, if it is 80th percentile, that means that 80% of the population of the data is below the value you've calculated. All right, so it gives you the relative standing. So instead of saying that somebody had 90%, okay, it's good, it gives us information, but we want to have information regarding the whole population. Okay, so we said that, okay, your mark is 90th percentile. That means that 90% of the class, okay, the marks that you got, 90% of the class got a mark that is below your mark. Okay, and then, so let's say that mark is, let's say, 56, all right? So that means 90% of the class got below 56, and then 10% of the class got above 56. Okay. So that gives you more insight into your data than just calculating the percentage of what the person had, all right? Okay, let's look at, so from there, let's look at interquartile range. Okay, so the interquartile range equals the 75th percentile minus the 25th percentile. So here we are looking at the space that is taking about the innermost 50% of the data. Okay, so we are not interested. So we know the 75th percentile, we know the 25th percentile. Okay, but if we want to focus on the innermost 50%, okay, that is when the interquartile range comes in. So if the interquartile range is small, it means that much of the data is close to the median. Remember here, we are looking at the middle 50%, okay? So if it is small, then much of the data is closer to the median. If it is large, it means that more of the data are spread out from the median, okay? If it is large, that means that more of the data is spread out. And the interpretation of whether something is large or small depends upon the kind of data that you have, okay? So there isn't a magic number that says that when you have this number, it is small, or when you have this number, it is large. So it is basically in the context of the data that you have, all right? Okay. And also, if something is large or small, whether it is good or bad, also depends on the data. So let's say that you are looking at income disparity, okay? If it is large, okay, we take a typical population. If it is large, it's somehow expected that, you know, if you have a huge population, there will be huge income disparity, okay? But let's say if you take examination score and then the IQR is large, that means that there's differences in performance, okay? So probably the teaching method being used is not the best, because you have some people who are at the bottom, people who are it's far from the mean. Okay, so it depends upon the context of the data that you are using. That will give meaning to whether a large IQR is large or not. Okay. So remember box plots. When we did box plots, when we were looking at our exploratory data analysis. Okay, remember I spoke about the upper whisker and then the lower whisker. Okay, so the 75th percentile. Okay, so that is the 75th percentile going. Okay, is the upper whisker. So that's 25%. Okay, above the how do you call it? Above the 25% above the quartile 3. Now, let me explain something here. So, you see, just a minute. Now, you see from the bottom, lower whisker, up to where at the bottom of the box, okay? Here is your Q1 or your quartile 1, okay? So I'll put some markers here later. Okay, so that means that below this is your 25th. So up to the quarter 1 is the 25th. The Q1 at the bottom of the box is your Q1. So this is where you have your 25th percentile. So that tells you that 25% of the data is below this up to the point of the line, okay, the straight line going bottom. Okay. Now your Q2 is the median. You see the horizontal line in the box. That's your Q2. Okay. And then your Q3 is at the top of the box. Okay. That is where you have your, that's your 75th percentile. Please, guys. Can you tell the person talking to mute? Please, can you tell the person talking to mute? I can't see because I'm sharing my screen.
No. Please mute.
All right. So the upper whisker is top 25% of the data. Okay. Lower whisker is bottom 25% of the data. Okay. And then the median is where you have the middle is the median. Now, in between the Q1 and then the Q3, okay, the top of the box and then the bottom of the box, okay, is where we have the interquartile rate. Okay, it's where you have the interquartile rate. Now, if you look at the box plots on your right, okay, you see that there is a data point. You see some asterisks at the top. You see the second box plot. Okay, so where you see asterisks at the top, that is higher than the maximum number. Here, you see the maximum number is up to where the line, the vertical line ends. Okay, at the top. Anything beyond that is an outlier. Okay, anything beyond that. So whether it is at the top or at the bottom, it is an outlier. Okay. Now, when you see these boxes, you see that the first one, you will realize that the box is evenly distributed. Okay, it's right in the middle. Okay, but it is spread. The second box, you see that it is much more compact. Okay, it's also in the middle, but it's much more compact. So this tells you that most of the data are near the median. The first one, okay, they are spread out from the median. Now, the third one, you see that it is spread to the top. And then the fourth one, the median figure is at the top a bit, okay, in the box. Okay, and then the fourth one, the median line is at the bottom a bit. Okay, it's closer to the Q1, whilst the third one, the median is closer to the Q3. All right. Now the third and then the fourth tells you how skewed your data is. Okay, if you have a look at it, let's have a look at this next slide. Okay, so now the one that is down here tells you the Q, you see the Q1 and then the Q3. okay, the first diagram at the bottom, the box plot at the bottom, you see that the median is towards, it's much more towards it's nearer to the Q3, okay? So if you compare it to the diagram above, on top of it, you see that majority of the data are on the left-hand side. So this is a left-skewed data. So when you see the median getting closer to the Q3, okay, it tells you that it has a long tail to the left. Okay, it has a long tail to the left. So this is a negatively skewed distribution or a left skewed data. Okay, now where you have the next one, where you have the interquartile range, but the median is near the Q1. That means that the data has a long tail to the right. Okay, so that tells you that it is a positively skewed distribution or a right skewed data. So your box plot gives you indication, as to the distribution of your data, okay, whether it is skewed or it is not skewed. Okay, so so the position of the median within the interquartile range will let you know whether the data you are dealing with is positively skewed or it is negatively skewed or it is symmetrical, in which case what measure of distance do you use in making your in drawing your conclusions or even making your analysis? Okay. Yes, yeah, you were asking a question.
Yes, Nana. So with the description that you gave earlier on with the performance of the class, there are certain times whereby there are outliers. People who, for instance, let's say they are in the class, there are people who perform outrageously, but majority of the class goes to one side. In such case, thinking about the interquartile rate, do we remove outliers from it, or we still consider everything?
So that is the more reason why we focus on the middlemost 50%. So you see that when there's an outlier, so that person will not be in the interquartile range. Have you seen?
Okay.
So if we are looking at the interquartile range, then the person will not be in. The person will be outside the interquartile range.
Okay. Thank you.
All right. Any question? So let's see how we can determine a typical outlier. Okay. So there's a mathematical formula for determining the outliers. Okay. So from now on, you know how it is calculated. So when you see an outlier, you see the mathematical underpinning of that. Okay. So the outlier, this can have big effects on the mean. Okay. So relying on them might give you a distorted conclusion. So the interquartile range is another way of measuring the spread that is less influenced by outliers, like I just explained. Okay. So in order to find whether we have an outlier, first of all, we need to determine the lower whisker, okay, and then determine the upper whisker. That will give us the maximum values to the left and also to the right. Okay, so you see the box plot, all right? So we have Q1, and then below Q1 to the left, okay, is the maximum number at the bottom. So you see where so you see the horizontal line, and then you see the vertical line to my left. Anything that is beyond this vertical line is an outlier. Okay. Now, when we come to the right-hand side, Q3 and above, you see from between Q3, there's a vertical line here. Okay. So between Q3 and that vertical line is the upper whisker. Anything beyond that is an outlier. So whether at the top or at the bottom, if any data point is there, it is an outlier. Okay. So how do we calculate the value between Q1 and then the minimum value? Okay. So if a value is less than Q1 minus 1.5 times the interquartile range, okay, or please just a minute, okay. Okay, sorry, I'm back. So here, in order to determine um, the value for the minimum number, okay, it is 1.5 times the interquartile range, and then you deduct from the Q1, okay, the lower the lower quartile. That will give you the minimum number. Okay, so the minimum number will be between that number to the Q1. If you want the upper whisker, that is between the Q3 on the right-hand side to the maximum number. Then it is 1.5 times the interquartile range. Whatever figure you get, add it to the Q3. That will give you the maximum number. Okay, so when you've calculated that, and also for the maximum number and then the minimum number, any number that is below the minimum number or above the maximum number is an outlier. Okay, so we have the 25th percentile, we have the 75th percentile, the maximum number, and then the minimum number. Okay, all right. So based upon that, you can be able to calculate the outlier. So based upon this, let's go back to our earlier data set. Okay, this one. Now, calculate whether there are any outliers in this data set. Okay. So do the calculation, whether there are any outliers in this data set. So first of all, calculate the 75th percentile. That will give you a Q3. Okay. Calculate your 25th percentile. That will give you a Q1. And then calculate the minimum value. That is interquartile range. Okay. Interquartile range times 1.5 minus your Q1. Okay. And then do that for your Q3. And then determine whether there are outliers in this data set. Okay. Go ahead. Please go ahead. I'm waiting for you. So for those of you who are able to calculate the 25th and then the 75th percentile, you can move on from there. Okay. So when you are done, let me know the answer, whether there are outliers in it, in this data set.
Hello, man.
Yes. Done?
Yeah, please, I couldn't find any outlier.
You couldn't find any outliers. Okay. Let's wait for the others. Well done. So how did you go about it?
Oh, no, let the others finish.
Okay. All right. Your position might change. All right. Okay. All right.
And I had similar to Ernest. I didn't find any outliers.
You didn't find any outlier. Okay.
I also didn't find any outlier.
Okay. So can you take us through how you calculated it and did not find any outlier? Yes, can someone take us through how you calculated, you went about your calculation?
Hello, ma'am.
Okay, go ahead.
Okay, so NSK.
Okay, and
So I started with the Q1, which is a 25%, 25th percentile.
Okay.
Which the actual value is 68.
Okay.
The 75th percentile, the actual value is 89.
Okay.
So I found the IQR, which is 21.
You found
interquartile range.
The interquartile range, okay.
Which is 21, the difference.
Mm-hmm.
So to find the outlier on the upper side is the Q3 plus the 1.5 times IQR.
Okay.
Which is 89 plus 1.5 into bracket 21.
So the maximum number was what?
120.5.
Okay.
But for the set, we are ending at 99. So on the upper side, there's no outlier.
So what was the maximum number?
120.5.
Okay. And then what was the minimum number?
36.5.
The minimum number was 36.5.
Yes.
Okay. All right. So all the scores were within this.
Within the two. Yeah.
Okay. All right. Yes, Delasi.
Please, I needed the slide that contains the formula.
This one?
Yes.
Okay, so I think the way you've done it is good. So first of all, you need to find the first quartile. Okay, that is the 25th percentile. Okay, and then the third quartile, that is the 75th percentile. When you do that, you deduct the first quartile from the third quartile. That gives you the IQR, that is the interquartile rate. All right. So after you've done that, if you want the minimum number, you multiply 1.5 by the IQR and then deduct from your Q1. That gives you the minimum number. Okay, if you want your maximum number to just multiply 1.5 by IQR and add to your Q3, that gives you your maximum number. So any number beyond the maximum or below the minimum is an outlier. So in this case, we don't have any outlier. So now you understand how the outliers are detected, okay, especially when we are using a box plot. Okay, so this is the mathematical foundation behind it. Any question?
Hello, sir.
Yes.
Sorry, can you please go over the outliers? How to determine an outlier, please?
No problem. No problem.
Thank you.
So we are looking at, but you understand the Q1 and the Q3, how we calculated it?
Yes, sir.
Okay. So the Q1 is the first quarter, okay, or the 25th quarter. The median is the Q2, that is the 50th percentile, okay? And then we have the Q3, that is the 75th percentile, all right? Now the interquartile range is the difference between the Q3 and then the Q1, okay? That is the range of those who are in the middle, okay? Now, when you calculate the range, okay, we need the minimum number, okay, to the left of the box. and then the maximum number to the right of the box. Okay, that will help us know. So with that, we will know the minimum, the Q1, Q2, Q3, and also the maximum. Now, any figure that is beyond the maximum or any figure that is below the minimum is an outlier. All right. And for us to get the minimum value, okay, we'll multiply 1.5 by the IQR. Okay. And then deduct from the Q1, that is the first quartile. And that helps us to get the minimum value. Okay. So in this case, I think the minimum value was it 36.5 based upon the data set that we have. Okay. And then the maximum value is, what we do is that you calculate 1.5 times your IQR, okay, plus the Q3, okay. In this case, you don't deduct, okay. So when is the minimum, we deduct from the Q1. When is the positive, is the maximum, we add to the Q3. So now we get the full gamut of the data set. So we have the minimum data set, the maximum, okay? And then, so the whole thing is the range, okay? From the minimum to the maximum is your range, okay? All right, so anything beyond the range, either minimum or maximum, is an outlier, okay? So that's how come we get our outliers.
Thank you.
Yes, Nanama.
Yes, sir, please, what you just said, can you kindly show it mathematically for me, like the question?
Okay, all right, okay. So let's work the question. So we want to determine the let's create one here. We want to determine the Q1. Okay. So the Q1, the first quartile, you know how to work the 25th quartile, isn't it? So we don't need to go through that. Do you understand how we work that 25th quartile? Okay.
Yes.
Okay, so what figure did we get? I think we got 68, is it not? Okay. And then the third quartile. The third quartile, I think we got 89. Okay. So 89. Yeah. So this is the 25th percentile. Okay. So we work the 25th percentile. The 25th percentile is what gave us the 68. Okay, we know that one, so we don't want to go through that again. And then the Q3 is the 75th percentile. Okay. So the Q3 is our 75th percentile. Or you want me to go through how we work the percentile? I can do that.
I'm okay with that one.
Okay, all right. So once we have the Q1 and then the Q3, let's calculate our IQR. Okay, so our IQR is equal to our Q3 minus Q1. Yeah? Q3 minus Q1. Our Q3 is 89. Okay. And then our Q1 is 68. So that gives us, is it 23? That gives us 23.
21.
Is it 21? Okay, sorry. 21, yeah? So for us to calculate our maximum number, okay, is Q3 plus, okay, 1.5 times the interquartile range. Yeah? And this is 89. That's our Q3 plus, or let's bring this down. That's 89 plus 1.5 times our interquartile range of 21. Does it make sense? Okay. So okay, so that gives us the maximum number. So 1.5 times 21 is what? Can somebody help us? That's about
31.5.
31.5. Okay, so 89 plus 31.5. Okay. So that gives us a total of
120.5.
120.5. Okay, so that's for the maximum number. So now let's check our minimum number. So our minimum number is Q1 minus 1.5 times IQR, yeah? So our maximum number now was Q1 was 68, wasn't it? So 68 minus 1.5 times our IQR is 21. What do we get? Please, what did we get? It's 31.5 minus 68, isn't it? So that gives us
36.5.
36.5. All right. So which means that our minimum number is 36. Okay. So our minimum number, our Q1 is equal to 68. Okay. Q2, that's the median, is 50%. Okay. So this is the median, okay? And then our Q3. So this 50%, it will be 50% of the data, okay? Okay. So we need to count and then look at the median in that case. I think it will be 77 or something. Okay, so or let me just write 50% middlemost number. Per the data, what is the median? Per the data set. Okay, I'll go back and then we check. So our Q3 here is it's 77, yes. So okay, yeah. So I was right. So that is middlemost number 77. Okay, so our Q3 is 89. All right. And then our minimum number is is 36.6. and then our maximum number is 120.5. Okay. So from our minimum number 36, okay, to our Q1 is where we have our lower whisker. Okay, so between 36 to 68 is where we have our lower whisker. Okay, our interquartile range is between the Q1 and then the Q3. Okay, our maximum value is 121. So in our data set, since we do not have any value that is less than 36.6 or above 121, okay, then there are no outliers in this data set. Okay. Please, any question? Any question? Any question, please? Okay.
Nana,
Yeah.
please, can we have an example of an exercise that maybe we have an outline we are supposed?
Okay, so that I will send you something, but for now, I don't have any example for now. I can get one probably in our next lecture, and then we'll work it
out. Okay.
But I mean, let's say if you were to have, let's say 5%, okay, 5% in the max or 3% in the max, probably this could have been outliers. Okay, I haven't checked it, but I'm just saying. Okay, right. Any other question? Any other question? So now we know how outliers, can be determined, okay, mathematically. Yes, Michael. Michael, are you asking?
So what it means is that with a set of data, you can have to calculate all these things that we've done.
You say? Michael, we can't hear you.
With a set of, I'm trying to say that it means that with a set of data, we can be asked to calculate all these things that we've done today.
Oh, yes. But normally, let's say you are using ggplot or something to plot the box plots and stuff like that. It will be doing the maths behind the scenes for you. Okay. So when it does a box plot for you and it's showing outliers, it has made the calculations already, and it's just visualizing it for you. Okay. But you have to understand what goes into the calculation. That is the main focus of this course. Okay. All right. So when you see outliers, it's not like you don't know how the outliers appeared. You should know the mathematical underpinning for such determination.
Thank you, sir.
Okay. So I mean, let's say in the exams you are given some data set to check. You wouldn't be given a large data set. The whole import is for you to know how to calculate it. Okay. So you wouldn't be given like 1,000 rows, and then you have to arrange them from the smallest to the largest. That will not be practicable. Okay. But something that is manageable, let's say 10 or 20 observations, I think that one you can manage that. Okay.
All right. Thank you.
Okay, you're welcome. Okay, so let's move on to other stuff. Okay. I put a Z-score table on the platform. Kindly download it, and then we'll take it up from there. Or you've downloaded it already. If you haven't done that, please do.
So we have it already.
You have it already. Okay. All right. So another way of looking at the relative standing, okay, is to use the Z-score. Okay, so the Z-score is a measure of relative standing of a single point in a data set. So here too, it uses the mean and then the standard deviation. So normally the raw scores are converted into Z-scores. When we do that, it helps us to determine the probability of a score occurring within the normal distribution. Okay, and then we can also compare two scores that are from different samples. Okay, so when you use a Z-score, you can compare two scores that are from different samples, which means two scores that have different means and then standard deviations. So let's see how we go about it. So a typical bell-shaped curve will have something like this. Okay, at the very bottom, okay, here you have your mean. Okay, you have your mean. All right. Okay, you have your mean. Now, when you go to your right, okay, that means that you are going away from the mean. Is that not it? Let's say you go one step to the right, you are going away from the mean. You go 2 steps to the right, you are going further away from the mean, and so forth. Okay. Now, the distance from the mean to wherever you are going, whether left or right, normally we use the standard deviation. Okay. So let's say if you go one standard deviation, so you are deviating from the mean, you are deviating from the standard. All right. So if you deviate from the standard by 1 point, let's say to the left, then it will be your mean plus the standard deviation, isn't it? Okay. So it will be the value to the standard deviation. If the standard deviation is twice, then you have twice the standard deviation plus the, wherever you were supposed to be. If it is 3 times the standard deviation, so the further away you go from the standard deviation, okay, the more error you are incurring, or the more the data that the answer they are getting is far further away from the mean. So normally, we've not done confidence intervals yet, but it is said that between standard deviation 1, that is between -1 or 1, okay, you will have 68% of your data within this range. Okay, now between standard deviations 2, okay, that is +2 or -2, okay, you will have 95% of your data between 2 standard deviations. Okay, now when you have 3 standard deviations, it has been proven to have 99.7%, okay, of your data within this range. Okay, there's a mathematical formula for this, but we are not going into this. Okay, but just for you to know. Okay, so a typical Z-score, okay, where you have your mu will be 0. Okay, when it goes to 1, it basically means your value plus standard deviation. okay, and when it goes to 2, okay. So we will calculate the z-scores, all right, and then it will help us to get figures which we can read probabilities into, all right. So the formula for the z-score is your value of x minus your x bar divided by x. Okay, so when we are talking about a sample standard deviation, don't worry, the x and then the row you are seeing here, they are the same thing, but one measures the standard deviation for a population, and then one measures the standard deviation for a sample. Okay, but the formula is one is S for a sample standard deviation, and one is rho for the whole population. So the z-score is your value for x, okay, minus S bar over the standard deviation. Do you remember? Have you seen this before? Last week, did you see this when we're doing the scaling? Do you remember? Hello? Hello? Please, are you hearing me?
Yes, you can be heard.
Yes, we can hear you.
Yes, sir. Yes, sir. We do remember.
But I asked the question that it's like the whole class is. Please, but I remember last week when we were doing the scaling, remember when we were saying that when you do data transformations and then I compared pounds versus height when we're calculating the Euclidean distance and said when you are scaling or you are standardizing, you deduct the mean from the actual value divided by the standard deviation. In actual fact, we were talking about z-score. Okay, so let's see how we can see. So for a bell curve, also called a normal distribution or a Gaussian, okay, 68% of measurements will have a z-score of -1 to 1. Okay, 95% will have a z-score of between -2 and 2, and then 99.7% will have a z-score of 3, or it has to be -3. Okay, so let's see how we can calculate. So let's say we have test scores for a class that is normally distributed, okay, with a mu of 75%, okay, and then a rho or standard deviation of 10. What is the probability that a student scored below 85%? Okay, so what we do is that we take the actual score of what we are looking for, all right? We deduct the mean, and then we divide by the standard deviation. Okay, so here our x, we are interested in the score of 85%. Okay, so that is our x. So we take our x to be 85% on your right. Okay, now our mean, the population mean here is 75%. So minus 75%. So you see the formula, the S, the observation of S minus the mean divided by the standard deviation. Okay, so here our X, we are interested in the score of 85%. So the score of 85% minus the mean score of 75%, all divided by the standard deviation. It gives us 1. Okay, now, so what this means is that when we get the 1, okay, we need to go to the z-score table. Okay, so let me bring up my z-score table. Just a minute. So our raw score now is 1. So we need to go to the z-score table and then determine it from here. So okay, so when we calculated it, we got 1, okay, positive 1. So let's see. So here we have 2 tables here. We have cumulative probability for positive z values, okay? And then we have that for negative z values, okay? Now, our score gave us 1, which is positive. So we use the positive 1, okay? So here, you use this table, the positive, for the one for positive values. So we want a score of 1, okay? So what you do is that you see the column Z, okay? So the column Z will give us the value. If there are any decimals, then we come to the right-hand side. But here we are just looking for 1. Okay, so let's look at the column Z going down and then come and check 1. So you see 1 here. Can you see? Please, let me have some feedback from you.
Okay? Yes, Nana, we can see 1.
Okay, so you can see 1.
Yes, Nana, we can see.
So 1 is the same as 1.00, isn't it? So under 1, we have 0.84. Okay, 0.84. So the interpretation is that the probability that people got less than 84%. Okay, remember that here we are looking at 85%. Here we are. What is the probability that a student scored below 85%? Now we've put 85% in the calculation, and we got a raw score, and then we went into our z-score table, and then we got 0.8413. Okay, so here we can say that the probability that a student scored below 85% is 0.84%. So there's 84% probability that a student scored below 85%. Any questions on this? Okay. Should I go over it?
Yes, Nana, please.
So
now we want to calculate our Z. Okay. Kindly mute yourself.
No, kindly mute.
So we want to calculate our Z. Okay. So when we calculate our Z, we go into the Z-score table, and then it gives us the percentage probability of that score. All right. So now we are interested in the probability that a student got below 85%. So now we are interested in the 85%. Okay. And then work out the probability that somebody got below that. So what you do is that you take the actual number of 85%, put it in place of the X. Okay, so that's what we have down here. That's 85 minus the mean. Okay, so the difference. So the difference is the error, isn't it? Okay, so the 85% minus the mean, okay, or the distance from the mean. So this one gives you 10. And then you divide by the standard deviation. So this one has been given to us already. Okay, so we divide by the standard deviation, and it is 10. Okay, so 10 over 10 gives you a z-score of 1. This does not give us the probability. It gives us the z-score of 1. Okay, so therefore we go into our z-score table, and then we go and find where 1 is. Okay, so supposing when we worked, we got 1.5. What will happen is that we will come to where 1 is here. Okay, where 1 is, and then we count to the left where 0.5 is, and then come down to where the level where 1 is. So supposing we work it and we got 0.5, then the probability will be 0.8531. Okay. But here's the case when we got the z was just 1, that is 1.0. Okay, so we take 1 and then we come under the column of 0.0, which is 0.84.13. Okay, so this gives us the percentage probability. All right. So now this is interpreted as the z-score, okay, the percentage probability or the probability of having a score below 85% is 84.31%. Okay, that's what this means. So if you want to calculate the percentage that a student got more than 85%, what will you do? Can anybody try? But in the first instance, do you understand this? The first one that we've just done. This one, do you understand?
Yes,
Yes, we do.
Please, the question again. Okay.
Okay, let's take another example. Then okay, before we do this, okay, before we take the work example, if let's say somebody got what is the probability that a student scored below 70%? Okay, so you work it now. Below 70%, based upon what we've done, just follow it and then calculate it. So what is the probability that a student scored below 70%? Work it out now. It's the same information. We have the mean and then the standard deviation. So work it out and then based upon your z-score, let me know. Yes, Delasi, you're asking a question.
Please, the z-score table.
Yes.
I wanted us to get access to it.
You say?
I was asking whether we could get access.
Oh, I've sent it. It's already on the platform.
I also have a question. What if it's above, let's say, probably the student scored above 70%?
We'll
Does that
come to
make
that.
any?
We'll come to that. Let's cement our understanding on this one, and then we come to the above. That will be our next exercise. So first of all, work on the probability that students score below 70%. Work on that one, and then let's see. Okay.
No, please. I think the answer will be 0.3085.
Okay, so how did you go about it?
I first calculated for the z-score, like 70 minus 75 over the 10. That will give me minus 5 over 10, like minus 1 over 2. And I converted into 1 over 2.
Minus 1 over 2. Okay.
That's minus 0.5. And I look for the minus 0.5 on the z-score.
Okay.
And
So when you go to the z-score, so
I
when you
went
go
to the negative.
z-score, you went to the negative.
Negative,
Good.
yes, please.
And then you went to 0.5. So where do we have it? It's here, isn't it?
Yes, please. So
0.3085. Yeah, okay. So that is it. So the probability that somebody scored below 70% is 30.6% or 31%. The last, your hand is still up. Okay. Okay, let's go on. Let's make other examples. So here, we find another practice question. So where this time round, the test score for a class are normally distributed with a mu of 70% and a standard deviation rho of 5. What is the probability that a student score below 64%? So now we are conversant with this, okay? So you take the 64%, okay, minus the mu, that is 70%, divided by the standard deviation. That gives you -6/5. That is -1.2. So we go to our z-score table. Let's go to our z-score table and go in. So this time around, we'll be looking at the negative side, isn't it? We are looking for 1.2. So let's come here. So we are on the negative side. Let's go to 1.2. So this is 1.2 on the z-score. Okay, so it's 1.20, isn't it? So in this case, which means we are going to use this probability. That's 0.1151. So the probability of scoring below 64% is 11.5%. Okay. Any question on this one? -0.12. Okay, let's see. Yes, it's 11.5. Yes, giving praise. Any question?
Nana, please, I wanted to ask if you are calculating it, do we calculate it in percentage or we calculate it then after that we add a percentage?
So your z-score will give you the raw score. All right. Yeah. Now, when you go into your z-score table, it's in decimals. All right. So when you are describing it, you can put it in percentage. So that means you multiply it by 100%, and then you interpret it as such. Okay.
Anna.
Yes.
And now what's the mathematical relation between the z-score and the probability table that we have here? Obviously, there was a relation used to generate these numbers.
Okay. What happens here is that this one is based upon this formula. If you see, yeah, normally they have that. Normally, there's a formula here for generating these figures. Okay, I can get it and give it to you. I don't know whether you want to go into that. Okay, so there's a formula. So you see that this one, the negative ones are normally, let's say, in the critical region of 5%. Okay, all right. Whilst this one, the positive ones are in the region of 95%. Okay, we'll come to that later. Okay, but I will find out if you are interested in the mathematical formula. I will get that for you. But there's a mathematical formula for that. Okay. Now, somebody asked the question. Somebody asked the question, if it is above. Okay. So let's say this one we have. What is the probability that a student score below 64%? Now, this same question can be asked as what is the probability that a student scored above 64%? Any suggestions? Any suggestions?
Hello.
Yeah, it should be obvious. Any suggestions?
I think you subtract this thing from 100.
Exactly, or from 1. Okay. So if below is 11.5, then above If you are using percentages, then deduct from 100. Then it will give you the other side. Okay, it will give you 89.5. So the probability of that a student scored above 64% is 89.5. Okay. You can even see it in the table when we go to the table. Okay. So the first one was negative 1.2, isn't it? Oh, how did we get the 11? Yes, it was negative 1.2. Okay, so that is below. Okay. Now, so which means the other side will be above, isn't it? So if you check, yeah. If you go to the positive, for instance, and they check 1.2, have you seen that we are getting this 88 points? Okay, so we are getting the other side, the above.
Okay. So in a way, the question is actually telling you whether your z-score will be negative or positive. So if the question,
so if it is negative, so if it is negative, you use the negative table, or you can even use the positive table and deduct the answer you get from one.
The answer from.
Okay, or you can go straight to the negative table and then use that. Okay, so this like a symmetrical. So whatever you have has its mirror on the other side. Okay. Any other question?
No. So there's not a question, it's a contribution about the normal distribution and the z-score.
Yeah, go ahead.
All right. So I use this for my daily routines that I do at work. And normally, if you look at the bell curve on the right side of it, it means that whatever you are monitoring is overperforming, and on the left side is underperforming. So with the z-score, there's a particular work that I do weekly, which I use this same z-score concept. Okay. Then remember you mentioned the 1 standard deviation, the 2 standard deviation, where we mentioned that 68% and the 95% and the 99.7% too. So I think that sometimes the application of what we are learning, how we relate it to our everyday life
work.
is what we will need to. But on that note, I want us to, before we close the class, talk about how the exams is going to be like. So that the exams then, because
okay. Well, don't worry, we'll have more time for the exams to discuss the
exams. Sure.
These are early days. This is your first lecture. You don't talk about exams like that. You scare people. Don't worry, we'll have a full session to discuss the exams. Okay, but thank you very much for your contribution. Okay, so please, what we have here, the probability of that the score is above 64. I've not worked that one, so you worked it. So just for you to know that what I have here is for the one that is below. Okay. So yes, yeah, please go ahead.
Nana, I understand the practice of the above where you subtract the percentage from 100. But when you went to the z-score table, you said you were looking at the opposite side of the z-score number, which was negative 1.2. That's why I got the confusion.
Okay.
Why didn't we subtract it from the total z-score to get the number before looking at the probability? But then we just look at the alternative number.
I don't get you. So the first one, when we calculated, we had negative 1.2, isn't it?
Yeah.
Okay. So the negative 1.2, we went to the z-score table. Let's go to the z-score table. So the negative 1.2. So we are using this, yeah? This,
yes, sir.
This bell-shaped curve. Okay, the one that is outside the critical region. Okay, so negative 1.2 gave us this. Okay, 11.5. Yes, okay. What I'm saying is that all the figures that we have here has its mirror on the positive side. Okay. So if this one, you deduct from 1, okay, its mirror will be on the opposite side. Okay. So you see that this one is 0.1587. Okay. On the other side, okay, if you deduct this from 1, okay, if you deduct this from 1, approximately you're going to have about 0.85 something, isn't it? Or 0.84 something. Okay. So when you go to 1 that is not negative, but 1 that is positive, okay, you see that you have 0.84. You see what I was talking about?
Oh, okay. Okay.
All right.
Okay.
So all of the figures have their, if you did that from 1, you have it from the other side. And so that's how the table is.
Okay. Understood.
Remember that, see, you have 5%. Let's say you have 5% here. Okay. And then if you come here to, you have 95%. If you add the 2, it's 100. So if you know one, you can know the other.
Yeah.
Okay, Ernest.
Hello, Mama.
Yes.
Please, since I missed something when you were explaining the score table. Please, why are we using the zero column? I'm
Okay,
sure
so when we calculate the Z, we get the raw values. Okay, when we use this formula, okay, we get a raw value of Z, that is negative 1.2. Okay. But this does not give us what the question was about, the probability. So it's the Z-score that gives us the probability for each Z-score. So it converts this Z-score into probabilities, so to speak. So that's why we are using the table. All right?
Sure.
What you go and do is that you go to the Z-score table, go and look for where 1.2, negative 1.2 is. It will give you the corresponding percentage, okay, in terms of probabilities.
Nana?
Right? Yes.
Yes, so I get that. Please, can you open the Z-score table?
Okay. There you go. Yes.
Okay, please, can you go to the top?
To the top?
Yes.
Yeah.
So I realized that all the questions we solved, we only take from 0.00.
Oh, no. So if let's take another question that might probably give us something like, that will give us something that is more than 0. I think that's a good observation. So let's take another example. I don't know what will give us this, but let's work for a situation whereby what is the probability that somebody will get below 43%? Let's work it and see. Below 43%. So work it, and then whatever figure you get, we'll go and put it in the Z-score table. So let me just probably create another one here. Oh, where is the 43%? Okay. So let me just copy this on its own. Yes.
The number you called has not answered. Please call back.
Blessings, kindly mute.
So let's work it for 43%. So that means that here will be 43, isn't it? The same information.
Yes, Nana, I think it will be outside the range.
It will be outside the range.
Yes.
Okay, so let's use something like 53%. Okay. So the same
And
information.
I think the percentage has to be in decimal for us to be able to get what is asking.
No. It has to work. Let's put it in there and then work it. Okay. 53%. Okay, so that means that this place will be 53. Okay.
Yeah.
53 minus 70 divided by 5. What does it give
Minus
us?
3. Minus 3.4.
Minus
3.4.
Minus 3.4. Okay. 3.4. Okay, so let's go to our Z. Is it 3.4 exactly? Is it 3.4 exactly or 3.4 something?
No, 3.4.
3.4 exactly.
Okay, I need something that is a bit more than 3.4. That's the main cause for using this. Okay, so let's use 49%. I want us to get something that is 2 decimal places. That is the input of what I want to do.
Hello. I'm saying that you look at two things.
So what do you get?
The money.
I think that's what Richard was saying, that unless we use a decimal place, the 49 gave us minus 4.2.
Minus
4.2.
4.2. Okay, so we should add a decimal to this.
Yes.
Oh, does it always have to be like that? Okay. In this time round, let's change the mu. Let's make the mu 65%. Okay. Let's make the mu 65%, and this one stays at 53%. So that means that this will be 53, and then this will be 65. Okay, what do you get?
Minus 2.4.
Really?
Yes.
Okay, use 67. Use 67.
And unless we use a percentage decimal, we won't get the.
Okay, let's use 67 and then we see. If it doesn't work, then let's make this, let's say 7.
Okay.
We have to change the standard deviation to get the.
We need to increase the standard deviation.
So we've made it 7 now. So let's see what we can
do. That's even worse.
What is it giving us?
Minus 2.
Minus 2. Okay.
Okay.
Use 6. Use 6. This on the go example. So let's try and error to see if we can get 2 decimal places.
Negative 2.333.
Okay, good. So we have negative
2.33. Repeating.
Okay, so let's make it negative 2.33. Okay. So what we'll do is that we'll go to our z-score. Okay. We go to, so our z now is negative 2.33. So let's go and find the probability that somebody scored below 53%. Okay. So this is 6. So this is 67. Okay. All right. Okay, so let's go to our z-score and go and look for negative 2.33. So this is our z-score. We have negative 2.3 here, isn't it? So we have negative 0.3 here. All right. So what we have to go here is to find the negative 0.3. The first one is negative 0.30, negative 0.31, negative 0.32, negative 0.33. Okay, this column. Have you seen?
Yeah.
So we work our way to where we have 2.3. So this will give us the reading for negative 0.233. Does it make sense?
Sure. I get it now.
Okay.
Thank you very much.
So when we come here, the probability is 0.99, isn't it? It's basically 1%. Okay. So the probability is 0.99%. Yeah. Any questions? Any question? Any question?
No question from my side.
Okay, Stephanie.
Okay. So please, you were saying that if we are looking at the probability of a student that scored above a certain number, we are supposed to deduct the percent. So for example, with this 53, so we are supposed to subtract 53 from 100. We have 47.
No. It's after you've calculated your when we calculated this the probability was now 9. So the probability that somebody scored above 53% is 1 minus 0.99. That will give you the other side.
Thank you.
Okay.
Yeah, but
are we okay?
No, sir. Sir, please, I still don't get it.
Okay.
Can you please repeat again?
Okay, so let me add that to this, and then we'll work it together. Okay, so this one, the one we worked here was the probability. Okay, then this one should be below. Okay. So the probability of a student scoring below below 67 is that. Okay. So this is, let's say this is A. Yeah. And then that one is B. So let's say this is A. So we've read the first one for A. Now, when we worked it, we got 0.99. That one relates to the A, that the probability that somebody scored below 53%. So if you want to find out the probability that somebody scored below, how do you call it? Somebody scored above 53%, then it's going to be 1 minus 0.99. Yeah? That will give you what? That'll give you what?
0.01.
No. Okay, sorry. This one, 0.01. Okay. So that means that the check this well. This one is 0.
Hello, Nana.
No. This, wait, just a minute. This is 0.99%. Okay. So remember that you are subtracting this. If you are doing it in terms of this, you have to bring 2 zeros. Okay. All right. So work it well. So it's going to be 99 point something. Yeah. Basically 99.1%. It's going to give you around, let's say, something like this. Is that not it? So that gives you about 99.
So now we subtract this percentage from 100 so that we
Exactly.
get
So
the number.
yes.
Okay.
Yeah.
So it will be, I think, 99.01.
99.01, yeah?
Yeah.
Yeah. Okay. Okay. So basically that's it. All right. So all that I'm saying is that the first one that we worked, we got 0 negative 2.3. That's working out to be 0.0099. Okay. In terms of percentage, it is 0.99%. Okay. All right. So that is the probability that somebody got below 53%. But if you want to check the above, then you deduct this from 1. That's what I'm saying. That then you can check the positive side. If you check the positive side, is 2.33. Okay. Check 2.33 under the third column. What do you get? The third column is here, this side. Okay. So if you check the third column, 2.33. 2.3, you see that it gives us 99.01. Have you seen? Okay. Yes. Give him praise. Yeah.
Nana, sorry. Please go back to the slide where we did the calculation. Yes, please.
Yeah.
Okay, please. So please, are you saying that when you subtract the decimal you had from the 1, you subtract it, you subtract it again from 100%? I don't know. Someone said that.
No. See, when we are dealing with probability, okay, it's either you are dealing with 100% in percentage terms, or you are dealing with the figure 1. Okay. So here, if you deduct, 1 minus 0.009, do it on a calculator. What is it?
I have 0.9901.
0.9901.
Yes.
0.9901. 01. Okay, this is the same thing we have in the table, isn't it? So this is the decimal. Now, if you want in percentage, you just multiply this by 100%. Okay. Then it gives you the 99.01%. Yeah.
Okay. So my question is, when you're looking for the above the percentage, we always calculate it like this, but when we are looking for the below, we just
so it depends upon the question. Let's say the question asked you, the initial question was that what is the probability that somebody got above something? Okay. Now, when your z-score will normally give you what is below. Okay. So if you're looking for what is above, then deduct from 1, it will give you the below and the above. All right. Okay.
Yes, please. Thank you.
Yes. Any question? Any question for today? Yes. Please go ahead.
Okay, so I have missed that part, but I want to put the in context so that I'm able to.
I can't hear you. Please.
Hello, can you hear
slow
me?
down.
Can you hear me now?
It's like you are slanging the tree. Oh yes. Tell us. What are you saying?
Yeah, so I'm saying that I want to understand something. Maybe I said that right. So if you look at the value of the z-score that we
All the machines running. Oh, 1 to 8. All the machines running.
She's not done, but she's still making them.
I'm saying all the machines running.
Yeah, with the exception of the one that you just compressed.
Well, what's the challenge?
Can you speak to your colleague?
Oh, please, can you hear me?
Yes, it's better now.
Hello.
Yes, go ahead. Go ahead. Go ahead.
Yes. So the question the point I'm making is, it appears the z-score is in multiples of standard deviation away from the mean value. I don't know if I'm wrong, but
it
appears to be away, so that if you get a negative z-score, then the value the percentage you are looking at is below the mean value, and those
yes, exactly. See.
the
I
mean
mean,
value. That is what
everything
I'm
is.
getting from the calculations we are doing so far. I
Yes.
don't know if
Yeah, it's the same thing. See,
I'm getting somewhere.
See the calculation. It's divided by the standard deviation. Okay, so everything that we are doing here is in terms of the standard deviation. The
Yeah,
raw
it appears to be multiples of the z-score.
Yes,
multiples of the standard deviation.
yeah.
So the question I'm asking is, it appears that if you have a value, a negative z-score, then the value you are looking at is below the mean.
It's below the mean.
And then those
it's going to the left side.
Above. That's what
Yes.
that's the understanding I
Yeah.
wanted. I wanted to be sure if I'm on the same. Okay, thank you very much.
Okay.
All right.
So you can even see it here in the table. Okay, you see the bell-shaped curve. Okay. This one. So you see that this one is left of everything, the Z, where it is shading. Okay. So you see that it is left of that. And then while the other one is on the other side. Okay, yeah. Nene, yes. Nene, you were the one that did not mute and you were disturbing some time ago. Please go ahead. Nene, your hand is raised though.
Yes, go up, man.
Are you asking a question? Okay, all right. Yes, Nanama.
Yeah, so I want to confirm something. Looking at what we've just done,
yeah,
I can see some reflection here. I think if you calculate for the below and you get the figure, you can use it to get the above on the probability table. Is that right? The
yes,
above.
Nana, that's what we've been saying all day long.
Oh, okay.
Because
without
it is
doing the calculation.
It is a mirror, yes. So if you know one, you can know the other.
That's without doing the calculation, the 1 minus the.
Yes, you can even know, yeah. So far as you know one, then you can know the other side too. Okay. It will even be more you will see it more in our next exercises, okay? When we are doing sampling distribution. Okay. And even down the line, when we calculate p-values, you can use knowing one to reduce for the other. Okay. So normally when we talk about normal distribution, it is symmetrical. That means that the data mirror itself. Okay. So when you're able to calculate something for one, you can get it for the other side. Okay. Okay. So let's wrap up on what we've done today. So data can be described as qualitative, that is nominal or ordinal, okay, or quantitative, that is discrete or continuous, okay, and both can be represented graphically. Okay, so we look at the measures of center, that includes the mean, median, and then the mode, all right? And then we said that if your data is skewed, okay, then it's much more reasonable to use your median instead of your mean, because if it is left skewed, the mean is drawn or dragged to the left. If it is right skewed, the mean is dragged to the right. So in such instances, you are better off using the mean. Okay. The measure of spread, we look at range, interquartile range, variance, and then the standard deviation. And then we use the z-score to determine the probability that a single observation could have occurred in a sample population. Okay. So if no questions, then thank you very much. I'll send the slides to you by this evening. Yeah. Any question? Okay. All right. So we'll continue tomorrow. Okay. And then we'll see how it goes. We'll build up on this and continue tomorrow. Okay. So thank you very much. Have a very wonderful weekend and speak to you soon. Okay. I'm here for the next 5 minutes. If you want to ask anything, you can do that. But other than that, we are done. So you can leave if you want.
Hello, Nana.
Yes.
Still on the examination.
No. Okay. You talk about it. I don't know why your examination.
It's important, Nana. You see, in the beginning, you were talking about us understanding what actually happens. For instance, if you take R into consideration, there are a lot of calculations and things that happen in the background. The point here is to really understand maybe some of the things we put out in terms of our analysis and stuff.
Yeah.
So I'm just curious to know why we must be calculating these things manually in examination instead of.
Have you seen the examination question?
No.
Then why are you? You've not seen the examination question. Meanwhile, you are complaining about the examination questions. So I'm just wondering. I need to go and check where I put my questions, whether they are.
Okay. Then check and come and give us feedback.
Okay,
and I also think that
and by the time you see the
some of us that are new to this kind of program, it's better we understand the basics and then what the.
Oh yes, so that is so wherever you are going to have calculations, is going to be simplified. Most of the questions you'll be answering, you'll be interpreting output. Okay. So please, this is a higher level. Nobody is going to ask you to calculate a mean and stuff like that.
So Nana, if I should be frank with you, it's today that I'm understanding the outliers and then the box graph and everything. So what we did in R, I can tell you truthfully, I'm now learning the whole thing.
Okay,
but today's
so it's good.
Has given me the understanding about
so if you see outliers, you see the underlying what do you call it, calculations that have gone on.
Exactly.
So that is the import of this program, of this particular course. Because most of the models will be building, okay, especially when we go into predictive analytics, most of the models will be building, okay, has statistical or mathematical foundations to it. Okay. So you will see how some of these topics, okay, if you've done it in the past, it was kind of abstract, but now you will see how these things are applied, practically. Okay, so it makes much more sense. Okay. All right, thank you. Yes, Christiana.
Listen, if I understand what you're saying,
Christy.
Please,
Christy always have the last word. Christy, go ahead.
Are we not going to keep formulas in our head to come and write the exams, right?
Oh, no. In the exams, I try as much as possible to give you some formulas, but some basic ones you are expected to know. So, but long formulas, please. I will give you all the formulas in the exams. Please, the focus here is not about few and poor formulas and come in. Please, that's not the focus. Okay. Just understand what you are doing, and then you'll be fine. Okay. All right. Any question? So if it is mean or anything, there will be formulas given to you in the exams. Okay. Right. Okay. Okay. Thank you very much, and have a nice day. God willing, we'll meet tomorrow. Okay.
Thank you too, Nana.
Welcome.
Thank you.